Great. Yeah. So I was saying, like, yeah, I got my PhD in Graz in Austria and spent some time at Carnegie Mellon as well. So here we go. So what do we do at Kodiak? We are actually working on autonomous trucks. And so we're trying to build the safest driver. We're starting with autonomous trucks. That's not all we do. You will see in my talk that we also started to work on national security last year. So we're working with the US Army as well to deploy some of the autonomous technology there. But really, the commercial trucking space is our bread and butter. That's where we started, and it's the first problem that we actually want to solve. So how does that look like as you go out and drive on the road? You have a lot of things that happen there. So people often think of it as like, well, you just follow this one lane. But if you look at the top right, there's, for instance, a house passing us. We often see windmill blades passing us. We see people riding horses across the freeway. We see in Texas, people walking along the freeway with their dogs, right? For instance, just taking their dogs out, where there's actually a particular area where there is the same person doing this every day. So you can't even say it's an edge case anymore in this case. So there's lots of things that you need to handle, from pedestrians to tunnels where you might not have GPS reception, right? We don't actually rely on any GPS or on any RTK. All of our algorithms are contained on board. And we do this in various different weather conditions, rain, fog, wind. We do it at night. We also have to basically reach rest stops that are close to the highway, which is how we actually operate this. We have human drivers bring in the trailer, and there we swap it onto an autonomous tractor, so the front piece of the truck, right? And then we go over many, many hours to another destination where, again, we stop and a human driver comes, picks up the load. So we're not just testing. Kodiak actually has by now the most extensive AV network of any AV company, right? This, what you see here, is about 18,000 miles of map, and we're driving that 24/7. More than 50 paid loads that are being delivered every week. And for really big customers, like, for instance, we have a multi-year contract with Kia. We work with 10 Roads Express, Werner, Siva Logistics, Sierra England. Sierra England has, for instance, one of the largest refrigerated fleets. So they transport refrigerated chicken, as an example. And that's where really to be on time and to be reliable is super important. And that's something autonomous trucking can really help with. So how does this look like from a computer vision perspective? I know you're all interested in the computer vision piece. So this is roughly how the system looks like. We actually detect, of course, a lot of objects around us. We know where the free space is around us. We know where all the lanes are. And notably, we run all of this without any HD maps, right? So we're one of the only companies, especially in autonomous trucking, that runs without any HD maps. And that lets us scale so fast to these many, many miles that you have seen. Usually, company have like hundreds of people to create a few miles. In our case, we have 3 people to create thousands of miles, right? So it's quite a difference. This is the talk that I gave yesterday, so I'm not going to go into it too much, but you'll find it in the recordings if you're interested. So what are we talking about today, and what is interesting in the end to make this happen? Well, we want to take the driver out, as you see here in this video, right? So here we have the driver actually, this is on a closed course, but the driver leaves the vehicle, and a few moments later, we can actually set the destination for where the truck should go, and the truck just goes and drives actually completely on its own. So this is working today. It is working in closed courses still, because we haven't fully built out our safety case yet. We can't yet prove that we're as safe as a human driver, but that's what we're working on. And when you look at that video, we published this a couple of weeks back, and someone posted it on Reddit, right? And you know how Redditors are, they would basically go in and criticize everything. And they would basically go and say like, well, this is not very very sophisticated, right? It's just following the road, right? It's not like, well, what is so special about this? And I realized that a lot of people don't really understand what's behind an autonomous vehicle and what you actually need to do to make this work, right? Because what you see here is really one of the state-of-the-art vehicles, because it actually needs to check a lot of other things rather than just staying in its lane. And so really my first takeaway for you today is like, when you do driver assistance, then nominal driving matters a lot. However, if you do driverless autonomy, then the edge case behavior matters most. And one of the predominant edge cases is actually faults that can happen in the hardware, in the software, in various different pieces of the system. There is no more driver to intervene, right? If something would happen to the vehicle has to deal with all of it. So what does that mean in practice? Well, these hardware and software faults, we actually need to handle them. And let's look at one. We actually went out and said, well, can we handle a blown tire? And so we have the vehicle here drive over a device that actually blows the tire, as you can see. And our truck handles that case nicely. We actually have what we call a fallback. So we come to a stop here in the road, and we're the first and only AV company that has ever shown that they can handle a blown tire. This is for a massive, large vehicle at highway speeds, right? So we can maintain precise control. Usually, if you look videos like this up, blown steering tire of a truck on YouTube, you will see that usually the trucks veer like 2 lanes over, they crash into a barrier, and nearly every trucking CEO of larger companies has actually lost a driver's life to accidents like this, because this is a very severe thing that happens, versus our truck can actually stay in lane because it has such a fast controls loop and can detect the problem very quickly. So lots of safety that we can bake in here, but we need to check it. And I know this is not quite computer vision directly, right? But you need to actually know where the lane is, and you need to actually detect all of this. So there's quite a lot of computer vision actually involved in this. So what is it that when we build platforms, and I want to generalize this also a little to all of your systems. I'm sure you all work on different systems, and they all have very similar components to what we have here. So this is our truck. It has cameras, LiDAR, radar, and here 2 different parts of LiDARs actually, one long-range scanning LiDAR and then a rotating LiDAR as well on the bottom. And in our case, we actually put all of this on the mirrors. We call these sensor pods, because that makes them extremely fast to upfit on trucks and extremely easy to exchange later on. So that's again something that is unique to Kodiak. No one else does this, but it really matters for a product, right? You want to be able to really upfit these vehicles and exchange them if one of these faults happens very quickly. So that's maybe on the hardware there. What do those sensors see? You see here that the cameras actually have a 360 degrees surround view with quite a bit of overlap to add redundancy. You have the radar field of view. It's a bit hard to see, but radar is hard to visualize actually. So you have a lot of small points there. These are imaging radars where you can actually go and see point clouds as well. And then you have the LiDAR field of view. Again, 4 LiDARs around there. This, what you see here in the background, this is always like actually the field of view, and the little red thing is the truck. So you see, you actually see quite a bit around the truck. So then we go on, right? And we have these sensor pods that I talked about. We also have a pretty big and beefy computer. And we have a smaller, what in automotive is often called an ECU, an electronic controls unit that actually interacts with the vehicle. So this is our high integrity computer that basically always needs to work, right? It never needs to let go of the vehicle, because otherwise you would have a truck that drives away, right? And so we're back at these faults. Whenever this computer fails, right, you have a truck that just basically drives down the freeway and being uncontrolled. So while we talk about, hey, we have to do the right behavior in terms of autonomous driving, right? This is actually very important. This is not what often appears in the different talks. And so if you go a little further, you can say, okay, so how about the autonomy software? Well, you start at sensing, where you see here on the bottom left, or all of these sensor points together. And then you run perception on this, and you actually get bounding boxes, you get like free space, you get all the things that I just showed you before, right? Then you do localization as well, so that you know roughly where you are, where you want to go. You have a goal in mind, right? You actually want to do a commercial delivery. And then you plan a trajectory, which you can see in green here. And finally, you send it to the vehicle. And that's where this little box comes in, where you say like, well, actually, let's make sure I always control the throttle, the braking, and the steering very accurately. So all of those components can have issues, right? Every single one. And every single one can make mistakes. So you want to limit how many you have. If you look at some autonomous vehicles out there, they have like, I don't know, 40 sensors on them. And every single one of them has a expected life. It has an expected failure rate, right? And if you actually look at 40 sensors all having a certain failure rate, the chance that one of them fails at any time is actually reasonably high, right? So the more stuff, and the same goes with algorithms, the more complexity you pack into these vehicles, the more chances you have that something fails. And ideally, you have a non-catastrophic failure. And we'll talk about what failures there are in a second. But these faults and failures actually need to be mitigated, right? And that's what, in a lot of talks that I have heard here and in other conferences, people don't really talk about, but it's super important to actually deploy a vehicle. So which faults are there? What can happen? We talked about this pipeline, and I'll focus mostly on those because you have seen, of course, the vehicle can have all kinds of things. You can have a tire blowout. You could have, I don't know, you're running out of steering fluid or engine oil, right? There's a ton of vehicle-related things that can happen. But we want to focus today on the autonomy pipeline that is closest to the computer vision parts. So you could have a sensor fail or provide wrong data. Actually, providing wrong data is even worse, and we'll talk about that in a second. You could have perception modules that associate the wrong pair of data. Let's say you actually have an image and you associate that with a LiDAR that is, say, 500 milliseconds old, which on a freeway is about 10 meters, right? In terms of freeway speeds. So you associate those two together and you say like, yeah, they match. And then you use them in like a frustrum net, or you use some net that fuses those together. Well, you'll get a very wrong result, right? So it matters a lot what goes together. A map could not match what is perceived on board. A planned trajectory has collisions because it's missing inputs. Let's say you never check that actually your new scene comes in and you're like, there's no one around me. Wonderful, right? Well, that wouldn't be good because you would actually collide with all the vehicles that you didn't perceive. And finally, you can also have what is called a latent fault. So let's say you actually did your homework and built a really good system, and you have two brakes that you can use, but you're only ever using the one brake, right? Then once this brake fails, you actually are trying to use the other brake, but you haven't checked that that brake works ever, right? So it might have been faulty all along, and you didn't actually notice. So that is what is called a latent fault. It's basically broken kind of in the background and you didn't know. So we run actually at Kodiak, we run more than 10,000 of these checks every single second, right? That's a lot of checks that need to be implemented and that actually need to be right. But that is what it is required to really build a safe system out there. So let's maybe talk a little about what some of these are. And again, I'm trying to show you that this is actually for a lot of robotic systems, a lot of embedded systems, the same thing applies, right? This is not just for autonomous driving. So individual hardware and software components, they sometimes have missing and late measurements. And as an example, you could have a network connection that is sometimes flaky or gets overloaded with other sensors. You could have a time synchronization issue. You could have operating system calls that every now and then, once in a million, right? Actually, they take a little longer. They take twice as long because there was something else happening on your operating system. That's where a lot of the real-time operating systems come in that you want to use. But even those have their limitations. You could have, for instance, a module, like let's say you have a car detector, and there's no cars around you, well, then it actually usually runs a little faster than if you're driving on a freeway and there's a car dealership next to you, right? And maybe in a traffic jam as well. So you see all the cars in front of you and you see all the cars of the car dealership, and suddenly your non-maximum suppression, if you use one, doesn't output like 0 object, it outputs 200 objects, right? And everything else in your system needs to run with that. So what can happen? You can actually, here you see as an example, you actually see a couple of CPUs that are all running different things. And you see the tracker here takes a little longer than usual. Now your planner actually has old input, right? So it will make the wrong decisions because it either needs to rely on what is a little older, or it basically just didn't notice and it didn't check at all. And in this example, well, you could say like, well, what do 100 milliseconds matter, right? But actually, on the one hand, you're building a safety case on some of these timings, right? What's your reaction time? But then also those actually stack up, right? So it can lead to what we just said before, where an image and a lidar that don't go together, they don't belong together, they get associated, and you run inference on that, and then you get results that you have never tested for, because in your training sets and test sets, you never had that problem, right? So what is something that you can do about it? Some research we would love to see is actually that people start to list their P95 and maximum run times of their networks, and they include post-processing time. A lot of times people, they pretend their neural networks actually take a fixed time and it's always the same. And they're like, well, we run it at n frames per second, right? Whatever it is. That's usually not true. That's usually an average. It is sometimes the best run time, right? So really understanding what is actually the inherent determinism of this method, what's really the bounds of it, that would be super useful if the research community could actually start doing that. Now you go on with timing, right? And you say, well, let's actually have a stack of these things. And I removed exactly what we do here, but there's different things in a pipeline. You can imagine in the beginning, you actually record an image or a laser spin, and then you go do some other parts on it. And towards the end, you get to creating a plan. And at the very end, actually, you send it to the vehicle, right? You say like, okay, I decided what I should do. But you see those actually stack up. And in this particular example, there's quite some gaps in it that you feel like, well, do they need to be there, right? Could I actually be faster? Could I do more things in parallel to actually shrink that latency and have a better reaction time? And yes, you can, but you need all of these debug tools. You need to actually look at all of that. And sometimes the failure modes here are like, you actually have your CPUs or GPUs taking longer every now and then. You get throttled because your GPUs get hot, right? A lot of that actually goes down to kind of to embedded vision problems that you see in the world. And so you might have I/O ports, operating system calls, again, that take a little longer. And in the end, you're actually delaying your braking, or you're creating, again, collision-prone trajectories because you had such a big delay in it. So again, what research would we love to see here? If people can develop, or if you can let me know after if you know of a framework like this that is actually efficient and deterministic multi-GPU deployment frameworks where the number of GPUs is smaller than the number of models, right? It's always easy to say like, well, I have one model and I run it on several GPUs. I just split it off and I do that. But really something where I can say like, hey, I actually have 10 models, but I only have 2 GPUs. How do I actually run this in a way that is repeatable and deterministic? That's not a simple problem and would be a very interesting one for the embedded vision community. Finally, of course, data integrity matters a lot. And so sensors can actually contain wrong representations of the world. And by wrong, I mean like the world actually doesn't look the way I see it in an image or a laser point cloud, so it's not reflecting reality. And you see here examples where we actually have some kind of lens flare problem that it creates a ring in there where you could maybe some image processing network could pick that up and say like, well, what is this? There's a big object in front of me, right? You can see here a laser point cloud on the right where there's a lot of points that are most likely not there in reality in this particular one. You see here on the where the red arrow is, if you see it here in this one, you see this black area, and it looks like the road is a little darker, right? That's not actually the case. This is actually a bug on the lens. This is how it looks like if a bug hits your camera, right? And so wherever you would drive, this would stay in this position. And if you have actually drive, this is not super dense. The light kind of goes a little around this, right? But you see, like if there is a pedestrian that actually fits this shape, then you might not really see that pedestrian if this is in the right spot. So really having a method that tells me, hey, this image has a problem, even if it just says like you should clean, right? We actually have cleaning hardware on our trucks. Even if it tells me just that would be super useful. And then over here, you see this little object here on the highway, right? Which is not actually an object. This just happened to us very recently, where this is actually a painting on the ground. You sometimes see those kind of these drawings that people do, street artists, right? It looks super three-dimensional. This is a natural one of those, right? It's not actually an object in this case. So those are really good. And when you can detect it, then you could clean the sensors, you could flag them as potentially wrong, throw the data away, be fine with some of the timeouts it causes. But if you cannot detect it, really the only thing you can rely on is redundancy, right? And so again, the research we would love to see in these areas is developing methods to better detect and categorize some of these sensor artifacts and the data integrity problems. I think this is actually a huge embedded vision research area that I think would be really cool to tackle. So we talked about some of these faults. So what is, and I talked about redundancy. When can I just rely on redundancy, right? You actually go, enter a field called systems engineering. Don't know how many of you are familiar with that, but it basically talks about how to set up a system the right way and how to run through the process the right way. There's different standards around this. One that is actually more for the hardware pieces is called ISO 26262 for functional safety. And that distinguishes between single point faults, multi-point faults, latent faults, and residual faults. And I already talked about the latent ones, but a single point fault is like the one thing breaks and your bad event happens. Your bad event could be, I lose control of my truck, right? As an example. You want to absolutely avoid those, right? You want to make sure you have none of those. So that's how you design these systems, that you make sure, well, at least multiple things need to fail at the same time for this to still be safe. But you will always have residual faults, right? Like you could actually, several things could fail at the same time. You just want to make sure that that likelihood is extremely small. And what you use for that is like failure modes and effects analysis, you use hazard and risk analysis, failure trees, like you see here on the right. These are actually kind of logical ors and ands, right? Where you say like, well, if this fails and this fails, then this is the outcome. And so you run through all of this for your system and you come to a certain likelihood that the system will fail or that it will not fail, right? And that is what you then use to create your safety case. So a lot of rigorous design and testing, actually, you can make a very structured safety argument on this. So some problems, of course, they can be fixed dynamically on the road. And at Kodiak, we have developed, for instance, for this map problem that I described. That happens sometimes, especially if you go on long journeys, right? The road just changes and we don't want to pull over every single time. Let's say we had a detector that says, hey, this left image here is actually in purple, you see the road, in green, you see what is detected, doesn't quite fit together. We can write a detector and say like, doesn't fit, pull over, right? That would happen on long stretches too often. And because of that, we dynamically fix this. So what we have created is a method that actually can dynamically refine the maps and creates what is seen here on the right side in red, so that we can then go and actually drive this. This data, as you see, we're not on a highway anymore. This happens to be for our off-road product that we're building as well. And importantly, though, you still need a localization fault monitor, right? We just made it less common, but it doesn't mean it will never happen. So you still need to know if you actually can't find a way of fitting your map of actually driving this, you still need to have a safe thing that you do, because you're driving a really large and heavy vehicle at speed, and you can't just say like, oh, I'm wrong, I give up, right? There's no I give up in that moment. You always need a next action. So how do we test a lot of this? We do a lot of fault injection using open and closed loop simulations. So open loop in this case means we have on-road data and we can actually run on that data. We can sometimes even completely synthetic examples we can run there. In closed loop in this case means we even simulate perception. Here on the right side, you see us go around the vehicle on the shoulder with various different hard lighting conditions, right? We on purpose created them this way so that localization would be hard, and that we could see, well, do we actually lose localization in conditions like this, right? Now we can go in addition, change the map, for instance, make it wrong, and then see, well, can we actually handle this? And so we run thousands of these scenarios every day, and for both these synthetic and on-road data. Also, of course, it's super important to go out in the real world and run the vehicle there. And you see that we put it through not only difficult scenarios, but also some shock and vibe. If you look at the left top image, we go over this bridge and then it's actually pretty shaky there. So the truck is getting a good shakeout. And that, again, that tells you what is going to break in terms of hardware, in terms of software, what's not working. So these iterations are extremely important, right? You actually want to iterate on that. And this is where I would say Kodiak is comparably to many AV companies, a small team. But this is where we can actually be super successful, because no matter how large your team, you actually need the iterations. So if the takeaway here again is like for your systems, if implemented correctly, many of the faults you can actually detect using timestamps, right? And data integrity checks. Or you can handle them dynamically even. It doesn't mean you always need to use your save maneuver that you have implemented. You can actually, in some cases, fix what the problem is, but you still need to detect it. So let's say we have detected one of these problems. What do? We have the system monitor that basically can say, well, everything's great. Let's execute the nominal plan. And this is what before you have seen as like a green trajectory, or it says, uh-oh, something did not go right. Let me actually execute what we call a fallback plan. So that can be stopping in lane, it can be pulling over to the shoulder. And so if we look at this, we actually did cut a cable here on the highway at 65 miles an hour because we're very confident in the system. We have tested it a lot, right? So this shows you how we immediately switch to this fallback plan, and the fallback plan pulls the truck, including its trailer, fully into the shoulder, and it comes to a stop here. So again, we were the first ones to do this, and we're checking about 10,000, so 1,000 signals 10 times a second, roughly to discover these conditions. But once you're pulled over, you're not done, right? You actually need to notify someone. You need to tell someone, hey, I just pulled over this truck. It has a problem. Here's what the problem is. And so we have an operations center that you see here on the left, where we know what the status and position of all trucks are. But also on the right side, you see our approach to sensor pods. We put all the sensors on mirrors so that they can extremely quickly be exchanged. And we can repair all of our trucks. Anything happens to the sensors within 10 minutes. Right. That is, again, is absolutely unique in AV in general, but especially in autonomous trucking, where it matters a lot. People want their trucks to be on the road, and we eventually get paid by the mile. So we want the trucks on the road as well. So to summarize and conclude, why and how do we do fault monitoring? It's actually critically important for L4 autonomous systems, but it's also super enabling if you do this for any other system that you use. No matter it's a robotic system or anything else, I would encourage you to go and actually check every step that you do along the way, because it saves you a lot of debug time, right? You will actually learn faster, you will have a much more streamlined approach, and you will discover new and interesting areas of research as well, where you're like, well, how do I actually detect this problem if it would happen? It's an iterative process. Oftentimes it needs actually real world data, because that's where you see what actually could fail. Sometimes we can't even imagine what could fail. And systems engineering processes like a failure mode and effects analysis or hazard and risk analysis, they really help discover new things that have never even happened, right? You haven't even seen them happen in the field, but as you walk through your system, you understand that, yes, this could happen and I should protect against it. So this is how you build a safe truck. and a safe autonomous system. And overall, of course, we couldn't do this without all of your research. So thanks a lot for doing this. We're building on the shoulders of giants here. And so please keep researching fundamental, but also applied topics. We value that research a lot. And please reach out if I can help with any of that, or if you're interested in working at Kodiak. We always are looking for great people in the ML, embedded vision space. So thanks a lot for your time.
Yeah. Is there any question? Please, yeah. Or you can speak loud. You can speak loud that people can hear.
Absolutely. Mm-hmm. Yep, absolutely. So let me repeat the question real quick. The question was, did we think about calibration? Does the system sometimes go out of calibration, and what can we do about that? So that is actually one of the big reasons why we use these sensor pods, because we believe that if this truck would have a problem, say in the middle of Louisiana, right, there's probably not a trained truck calibration technician there, right, who actually knows how to calibrate radar and cameras and LiDAR. So again, it's unique to our system that these sensor pods come pre-calibrated. So someone actually pre-calibrates them somewhere else, and then you can just put them on the vehicle and they are already calibrated. And if they are also, one of the checks, I told you there's like 10,000 checks, right, running per second. One of those, or several of those, actually check all the sensors for their calibration as well. Yes. Mm-hmm. It's a software check. Yeah, it is. It's basically making sure that all the sensors are well aligned, right, at any given point. It's essentially you're running your calibrations, and so you can create a check that does compute your alignment, your reprojection errors, all of that. Yeah, that's right. Say that again. Is it? That depends a little on the sensor, but in most cases, no, we don't need to. But that depends on the individual sensor, I would say. Yeah. For most of them, like we have metrics for all of this, right? And we basically just check, are the metrics working well enough? And if we don't have to do it, we're not going to do it.
Maybe I'll do one. What is the proportion of your training data that's synthetic versus real?
Mm-hmm. We have synthetic data for special classes that we don't encounter too much. But most of our, I would say, the majority of our training data is actually real, because we do get a lot of miles from driving for customers who pay us for those miles, right? So it's pretty easy for us to accumulate those miles. And whatever you see there, for instance, cars, we don't have any synthetic cars, right? Because we don't actually need to see them. There's such a lot of diversity out there on the road as well. It's more about identifying which cars are easy to detect and which already fit your distribution versus which ones are kind of outside of the distribution. So it helps to look all of that, like classical shaping of your data in machine learning. But for the synthetic data, you really need to make sure that it actually helps your classifier. And that is something that we definitely have looked into, but only for a few classes, it actually did provide a lot of value.
You also mentioned the ISO 26262 standard. Are you following the standard, and what are your experiences?
Yeah, so maybe to summarize this real quick, since we have a minute, in the US, so it's a little different in the US and in Europe, as an example. So in Europe, I'm from Austria originally, but I live here in the US, and I always use this example where I was at the swimming pool in summer 2 years ago or so, and the slide was actually closed, and there was one guy going down the water slide, right, a couple of times. I was like, what is he doing? And he was actually measuring how fast the slide is, and because he's from TÜV, and TÜV is actually the certifying body there in Europe. And so you can go, TÜV basically comes to the pool and says, yeah, your slide is certified. And then essentially, if someone hurts themselves, there's not really any legal basis that they have anymore, because the slide was within bounds, essentially, right? And so that's the system that people would use in Europe, and they would go there and they need this approval. In the US, it's different. We could actually, from a regulatory point of view, we could launch today. We're just not yet ready from our internal safety case, right? We know that our own bar is actually higher than this still. But that also means, to address your question, we don't need to follow any of these standards. So we can pick and choose what actually makes most sense, so that we really, in the end, build a safe and defensible system where we can go and say, look, we built this to the best standards that are out there. So yes, we do follow quite a bit of ISO 26262, but I wouldn't say we build our entry system just to ISO 26262. We have UL 4600 and various other standards, SOTIF, and that we look into and take for the right parts.
I have two quick questions. So the first one, what about the weather conditions? So we saw a lot of sunny roads and so on and so forth. But do you have like a high statistics on fault when it is rainy and snow? And are you dealing with this as well?
Yes, we do deal with rain and wind quite a bit, because on long haul routes, you can't pick your weather, right? In trucking, you need to drive in any of those. Snow, not that much yet, because we're driving in the southern United States where there's not a lot of snow. And so, but rain, absolutely, we do deal with.
And then the second question, I remember like 15 years ago, one was speaking about 2025, we will have the real commercial, autonomous driving trucks or cars and so on and so forth. But I understood that the certification process to get it out is a very complex, especially what you are doing now, like try to detect fault autonomously. So do you know how, like, what do you need to certify this to get it like commercially available, and like you can show that you can go to this fail-safe mode, which is really great invention that you are doing here.
Yeah, thank you. So in the US, we don't need anything. We could literally launch today, right? If we would declare we're ready, we could launch today. There is no certification process that we need to go through that takes many years. In Europe, it would be different. But here in the US, that is actually possible today. However, if anything happens in the US, then you get sued for that, right? And you have to show that you actually designed this to a state of the art. And this is what companies here in the US are working towards, to basically show that they can make their safety case, that they can actually demonstrate that they're safe in these environments. So and that still takes a long time, like you said, right? But it's not some certifying body that you need to wait for. It is a lot of these maybe nitty-gritty details, right? It's a lot of the grinding of like, what are actually the faults that can happen on a vehicle. Every time you change some of your hardware, software, how they interact with each other, you might introduce new faults or change them slightly, right? So there's a lot of verification and validation, as we call it, that goes into this, and where you go through this process and say, yes, this is actually safe.
But just a follow-up comment. In US, you don't need certification, but do you have to provide like a report that you drive, I don't know, 100,000 miles and you have this and this fault? No, you don't. Okay. So
no, you self-certify, and there's no formal standard of how you have to do this.
Okay, I see. Okay.
Yeah. There's for some of the permits that you need in passenger vehicles here in California, they ask for specific data, but it's very high level. For instance, you see this like Waymo and Cruise are applying at the moment in California for like a certificate that they can bill customers, and for that they need to actually show some of their safety records.
I see. Any last question? No, thanks a lot, Andreas.
Okay. Thank you.
welcome the next speaker, Ethan. Yeah. Yes.
Thank you.
So Ethan will talk today about uncertainty in real-time semantic segmentation embedded system. So really looking forward to your talk, Ethan. So
Thanks.
floor is yours.
Yeah.
Just need to share it.
Okay, we're good. Hey, cool. Howdy, team. Thank you very much for coming along. My name's Ethan. I'm from Queensland University of Technology, Australia. I'm a PhD student, just about to wrap up. But here I'm going to talk about some work that I've recently done trying to quantify uncertainty for semantic segmentation. So I'll talk about sort of how I do that, but why it's important. So why I'm looking at semantic segmentation in particular with time operations. So there's been a lot of work to try and quantify uncertainty like in deep learning models, but they aren't really sort of targeting, real-time operation. And I'll talk about why they aren't targeting real-time operation. Turns out it's really, really hard. So I'll sort of talk about a way that I'm trying to do it. I'll show you some pretty pictures with some experiments, and then I'll sort of like finish it up, maybe talking about some ways that we can improve upon it. So what the next sort of steps I think are, and sort of addressing how we can actually like build upon this uncertainty information. So how we go from uncertainty sort of quantification to some of the like planning that Andreas was just talking about and sort of delivering it, sort of acting upon like this important information. So we'll start off with why. So why I'm interested and hopefully why you're interested in uncertainty quantification. So just a quick picture. So here's a video, a set of some of the experiments that I was looking at. So this is like the end result and the different types of uncertainties that I can quantify. So here I'm looking at semantic segmentation, targeting autonomous vehicles. So on the bottom, we got our input image. We can see there's a bunch going on. We've got our predicted sort of quantities. So doing the semantic segmentation, we've got different types of uncertainties that we can quantify. So we have epistemic uncertainty. So that's sort of quantifying, what uncertainties are present within our model parameters and how that actually propagates towards our predictions. We can also represent aleatoric uncertainty. And that's sort of like trying to represent, what uncertainty is actually present within our data. So, if we had like infinite sort of data, hopefully we'd be able to reduce this to 0. That's not the real world. We live here. So we will have some uncertainty there. But then also, trying to have a look, hopefully you can see it there on the right, some class conditional uncertainty. So like what we might care about uncertainties related to different classes a little bit more. So, here, like I obviously, like if I'm designing, an autonomous vehicle system, I don't want to hit people. I want to sort of, maybe avoid them. If there's some like uncertainty related to the semantic segmentation there, maybe I want to incorporate some of that into the decision-making process, moving forward. So hopefully that's, a bit of motivation why we might be interested in this type of stuff. And we also need this to run in real time. Like you're driving an autonomous vehicle, can't wait around. You don't have, 10,000 GPUs to throw at this. You just got what you have on board. So we need to do this quickly as well. So why other methods aren't doing it, or like why it's sort of like hard to do. The most natural way to sort of, quantify uncertainty is, through a Bayesian perspective, where we'll sort of quantify all we know about our parameters and from our, like that, like quantification of everything, refer that back to, what we don't know. So like where the uncertainty actually lies. And the most general way to do that, with any type of real probabilistic perspective, we have like a probabilistic representation of what we're interested in, but then we want to compute expectations. The most general way to compute expectations is with Monte Carlo integration. That's slow. So like here, like our f of x here, that's sort of like our actual like feed forward network. And here, on the bottom there, like to compute, a Monte Carlo, approximation of our variance would require, say, like n forward passes of our model. So say if like it takes, we get 30 frames a second, for a device running in real time, and I want to, compute a variance with 10 samples, I now have like a feed forward time of, 3 frames per second. So like it's really expensive to do this in real time, well, for real time operation. You can do it in training if you want, but you don't want to do it for real time operation for predictions. So you don't need to worry too much about the maths. There'll be a little bit of maths here, but the main thing is just looking at these summations and the absence thereof, because what I'm trying to do is develop a way to sort of quantify uncertainty with no Monte Carlo integration when we're actually doing predictions. Okay, cool. So I'll talk about, how I'm trying to do it. So just to give you a brief overview of what I'm trying to do, we can't do, say, like full, Bayesian inference, over our model, because that requires, going towards a Monte Carlo approach. So what I propose doing is sort of breaking it up, do deep deterministic feature extraction, just this big block here. And this can be like pretty much any base network. So I'll show some experimental results where we sort of translate from, different base networks to a bunch of different, other methods output. So we can actually, get our probabilistic output. So here is where we actually have like a probabilistic segmentation head. And the way that I've designed it, I can sort of get like a predictive quantity, predictive distribution with no Monte Carlo integration. So that's what I'm trying to do, reduce it to a simple like operation where I can, build upon analytic solutions, make it run real fast. And then I also need to like propagate that to, final, pass it through a softmax to get the final segmentation. I propose, like a modified softmax model that'll actually allow us to do that too. Okay, cool. So here, just a little bit of maths, just to sort of describe like the model. Here, like this top line, this is like the deterministic sort of like backbone, like the deterministic sort of feature extraction. I'm then sort of passing that into like the probabilistic segmentation head. And then it's going to go, so like this alpha here is our logit. And then, going through a softmax, if we're all familiar with that. And the idea is to do probabilistic inference, for like the final classification or segmentation head, and then sort of propagate those uncertainties that are generated within our logit, like over towards, the final classification target. So that's what we're trying to do here. So we're having, creating, like a conditional distribution, for these parameters for like within our classification or our segmentation head, then propagate those uncertainties towards the output. And the way that we do it this way, it means that we can sort of reduce it to a linear operator, which means I can appeal to analytical results. So like I can sort of compute the integration analytically, no Monte Carlo integration, we're happy. So this is just talking about what it's looking like. I'll probably skip this slide for now, but the main idea is sort of like what I was looking at. We're computing, we're doing our probabilistic inference for our logit space, and then we'll sort of, transfer like the uncertainties in our logits over towards the final classification target. And this is just the model. Like this is just to say that it's normal. It's like it's a Gaussian. So I've created this way, so it's Gaussian. Means I love Gaussians. You love Gaussians. Nice analytical properties. Let's exploit them. Hey, cool. So this is why I want to like work with Gaussians, is because you see here, like this is like a final quantification for within our logit space, at least for, a variance in our, say, like predictive outputs. And you'll notice here, there's no summation. And that's really what I want, is that I can do this within a single forward pass. So there's no sort of need to sort of, run your model multiple times, just run it once and I can sort of, compute this integral, and that I can get, a quantification of, what I don't know or what I'm unsure about, in the final prediction target. So that was in the logit space. I need to then propagate that to a final classification. So the normal softmax isn't going to let me do that. But building upon, some of the assumed density filtering approaches that are out there, and say like expectation propagations, I'll sort of, create a way to sort of approximate, if I give it a Gaussian input, this is approximately like what the distribution would look like on the, on the output of the softmax. And again, no summation here, or at least for the denominator of the softmax. You do that in normal models anyway, so that's fine. But this is sort of like, again, a nice Gaussian representation of the output, which gives us nice sort of like properties. I can sort of, look at the class conditional uncertainties, like just straight away, just through the marginal distributions. I can just sort of look at the class that I'm interested in, and things work out really nicely, really quickly. And just to, recap, let's have one last look at the picture. So we got our input, deterministic, sort of feature extractor. This can be pretty much like, I used a bunch of different pre-trained networks. I'll show you some results now to sort of show you that it's a pretty general approach. You can use pretty much whatever you want. Then we'll have, a probabilistic segmentation head. So here, just like a single sort of convolutional layer that I can sort of then use to propagate uncertainties to give me an output in the logic space. So a mean output and a variance on the output there, just like with nice analytical properties. Then we got, a new softmax module that'll sort of propagate those further to the final classification target. Okay, some experiments. It's just to show you, prove to you that it works in practice. Some numbers, I don't want you to worry too much about them. So what I've got is a bunch of different networks, just to show you that it works for a bunch of different backbones. So you can sort of make, existing models, uncertainty aware. The main thing that I want to show you is that, I'm comparing, say, like a normal BusyNet version 1, and then a Bayesian version of it, which is like my proposed model. The main things I want you to look at are, that the predictive performances are comparable, and that there is only like a slight sort of, drop in predictive time, which is really what I'm trying to get. So, like I'm pretty much getting the same predictive sort of power, haven't really made any compromises there. And I've only made like the smallest sort of, like a reduction in prediction time. So it's roughly about like 15% across the board. Whereas again, if I was doing a Monte Carlo integration approach with 10 samples, it was essentially 1,000 times slower, 1,000% slower, 10 times slower. So some more pretty pictures. Whenever I give a talk, if I have an opportunity to show a picture of a dog, I'm going to do it. So that's what I'm doing here. So this is just to show that it's, not just autonomous vehicles. There are other systems that, need to operate within the real world. So like autonomous systems, are one of them. So this is just like another example to sort of show you that, yes, we can sort of do the predictive uncertainties, the predictive segmentations, get the nice uncertainties that we care about. And actually, having a look at more class conditional uncertainties. So we can sort of see, where in the actual segmentation target am I sort of unsure about? And what we often see is that we're going to see more uncertainties towards the edges of our targets, which is generally what we expect. But we want to be able to make sure that we can quantify this, especially if we see something new. So some weird edge cases, we sort of want to be able to, act upon them, in an informed manner. I've got some more examples here looking at class conditional uncertainties. I apologize, it's probably a bit, hopefully you can kind of see it here. But this is, again, from more autonomous vehicle systems. We're here looking at class conditional uncertainties for cars. And you can see, okay, like it's getting, most of the uncertainty sort of targeted towards, the actual like edges of the cars. Similar things for looking at vegetation, and road boundaries. These are all things that you care about. You don't want to hit trees. You don't want to drive on the footpath. And you don't want to hit other cars. You want to know where they are. So, and then here, having a look at more class conditional uncertainties, more doggos. So I want to see there's a car hiding in the back. Where's like the uncertainty related to the car's class, to the class car. We can see that it's sort of, targeting it. It's representing uncertainty like at that region of interest. With the dog, we can see, it's highlighting, where in the dog, and then also in the frisbee. So it's sort of giving us, some nice important information to sort of see, like, is the uncertainty coming from like the target of interest, or is there maybe like other regions in the inputs that's sort of, generating uncertainty there? So it gives us a way to sort of like calibrate, is our model sort of like performing how we want, or is it sort of maybe picking up on some things, that we, maybe don't want to see. Hey, cool. So that's just walking through my model. Just a quick recap. So like what we tried to do, combine some of the existing, say like models, just with deep feature extraction within a deterministic, like use that as a deterministic backbone. add on a probabilistic segmentation head and show how we can actually do that in real time, because that's really what we care about. All the experiments shown, we're looking at, doing it on a Jetson board. So working with embedded systems, doing it in real time, that's really what we care about. So we've got a way to do all that. What's next? So I'm now, I've been looking at, doing it, with a deterministic classification or deterministic feature extractor. I want to do treat everything in a probabilistic sense if I can. It's expensive to do it now, but I'm looking at some, ways to approximate that and to sort of, make the entire model uncertainty aware. And then importantly is to how to actually use this uncertainty information. So again, with real-time systems, we need to do things quickly. So, even if I can give you this uncertainty information, in a fast way, you need to be able to say, process it, act on it, and do that, all within the hardware constraints that are imposed, and say, use that to make meaningful decisions. So that's, non-negligible compute overhead as well there. And just, the difficulty of say, incorporating, a statistical decision theory approach, how to actually, mitigate some of these, challenging circumstances that pop up in the real world. And that's it. That's just talking about, that's a link for how I did the sampling approach. But yeah, that's pretty much it. So thank you, everybody. Thanks.
Probably some questions.
Thanks for the talk. Can you maybe elaborate on how you exactly train the uncertainty? But because I didn't really fully understand that from the presentation. So I understood that you have two outputs, the mean and the variance,
yep,
or standard deviation. But how do you train the standard deviation?
Okay. So the way that I'm doing that is I sort of skimmed over it, just the time. So what I'm doing here is I'm having a probabilistic perspective of omega here. So that's the parameters within my segmentation head, and how I'm actually getting, say, a variance, approximation for those is just through any type of sampling procedure. I want to sample the posterior of this. So I can do this pretty much with any sampling approach. I could use variational inference approach. I wouldn't go for that if I could avoid it. So I can use any sampling based approach. So I could use, say, stochastic gradient Langevin dynamics. I could use a full, HMC method if I'm interested. But what I did is just use the diagonal swag approach. So largely just because it's most amenable to existing training procedures. So I can use, stochastic gradient descent iterates, directly, so measuring, the variance amongst the different sort of, parameter samples that are given during training. I can measure a variance across them and then use that as a variance for my parameters there.
So you're sampling the weights?
Yes, yeah. Yeah, so. Yeah.
But then you still do a few forward iterations of that head?
No, not during prediction. There's only one forward approximate. So that's it. The idea is that if I was to, yes, only once. Yeah. We need to do multiple samples during training. And so we're fine to do that during training. Yeah. Take as much time as you want during training. I care about real-time predictive performance. So sorry. Yeah. Yeah. No worries.
Any other question? Otherwise, let's keep a hand.
Okay. So, could you please talk more about the uncertainties, the evaluation of the uncertainties? Do you have any metrics to evaluate the correctness of uncertainties? How do you know that the uncertainties that we obtained is correct?
Yeah, I'll just repeat the question because it's a really good one. So how do we actually quantify, if our uncertainties are correct? And there's no sort of quantitative sort of analysis here. And it's largely missing a lot from the literature because it's really hard to do. And it sort of depends, on where you're sort of willing to accept uncertainties. And it's sort of dependent on the actual, context and the task at hand. But it's something I'm actually looking at with some of my other research. Maybe I'll get a chance to talk about that. If anybody is interested about some of the sort of thoughts I have about that, you can sort of maybe ask me in the break. But it's a very good question. Yeah, thank you.
Thank you. Thanks, Ethan.
Thanks.
So we go to the next speaker, Sumana. Yeah, you are here. Yeah, perfect. title is Fully Binarized Distance Computation Based on Device Few Shot Learning for XR Application.
Hello everyone and good afternoon. So actually I'm Syed. Manan couldn't make it here because of some travel related issues. So I'm filling in for him. So I'm one of the collaborators in this work. I'm from the Meta Reality Labs research, and this is our collaboration with IIT Delhi. So yeah, so I'll be taking you through the talk. So this is the outline for this talk. First, I'll talk about our motivation for this work. Then I'll briefly go over the proposed binary distance computation algorithm. And we will show some results of the prediction quality for statistical validation of this algorithm. We did some ablation studies that I'll also share. And then we deployed the algorithms in embedded platforms to measure the power performance. And finally, before concluding, I'll share some projections on RM-based in-memory compute platforms. Okay, so in the XR space, where we look at augmented and virtual reality or mixed reality use cases, they heavily depend on some of the applications, tracking applications like eye tracking, hand tracking, 6 degree of freedom, position tracking, etc. And with the advancement of machine learning, these applications are heavily relying on like advanced machine learning, or also known as deep neural networks or deep learning. So these applications require like huge models and very large data sets to train on. However, we need to deploy these algorithms on really edge hardware, like extreme constraints on power, performance, area. So I don't know if you think about our existing VR or AR headsets, they have to be very lightweight. They are mostly portable, so they cannot consume much power, and it has to be real-time operation to give a good user experience. So for all these constraints, we have to be very careful about these tracking applications, which are almost always on. At the same time, to give a good user experience, these models should be adapted for the user. So to adapt for the user, it has to be either retrained or like marginally updated based on some new user samples. Now, this is also very difficult to do on device because either you need to train the whole model from scratch, or you have to use transfer learning to learn last few layers, but at the same time, you need the larger data set, which is infeasible on device. For this, people have been looking at different ways to adapt the model to the user, and few-shot learning is one of those approaches. In this work, we focus on metric-based few-shot learning approach, and it helps us to reduce memory storage, address some memory bottlenecks, and reduce power dissipation. Now, for metrics-based few-shot learning approach, we use a frozen network, and we store embedding features generated from the feature extractor, which are later used for classification or regression at the end layers. Now, in this work, we target both algorithm and hardware realization perspectives for this few-shot learning on device. And to the best of our knowledge, this is the first work that simultaneously addresses algorithm aspects and hardware implementation challenges, as well as in-memory computing based implementations. We propose a binary distance computation algorithm for the feature matching for few-shot learning. So I'll try to explain the algorithm on a high level. So as I mentioned earlier, we store some feature embeddings, which we call support vectors. And then we take input vector as query data. And our goal is to match the input with the support data. For that, first, we normalize both of them. For normalization, we use two different methods in our experiments. One is using mean and max values same for all the feature layers. And the second one is layer specific parameters for normalization. Once we have normalized the query vector and the support vector, we convert them to integer values and then use thermometric encoding to represent the vectors in binary. The benefit of thermometric encoding is that each of the bits are now can function independently, and we can use unary logic operations for those bits. However, we still use the same number of bits that was used for the integer representation. And once we have this binary representation, we can apply Hamming distance measurement to get the similarity matching. If the Hamming distance is lower, the match is higher. And for that, we can use logic XOR operations. We can also use XNOR. In that case, it would be inverted result. So using our algorithm, we applied this on tiny image, mini ImageNet dataset, and we tried 6 different variants to analyze the results of prediction or similarity matching. Here in the figure, you'll see those 6 different variants. The first row is for our normalization method 1, and second row is for the normalization method 2. And in the columns, we have different precisions for the vectors. Like first column is 2 bits, the second is 4, and then 8 bits on the third. And the outcome of this analysis is as we increase the bit precision, the separability increases. At the same time, normalization method 2 works best for even 2-bit or 4-bit precision. So this t-distributed stochastic neighbor embedding analysis method gives us very good idea how the algorithm works for the similarity matching between the query data and the embeddings. Once we got some idea about our algorithm's quality, we tried to do some ablation study to see if it can be generalized well. So for that, in the first table, we show results for different backbone workloads. So we use 2 popular workloads from literature. One is the, let me see if I can use my cursor. Okay, yeah. So the first one is a protonet or prototypical networks, and the second one is FEAT or few-shot embedding adaptation with transformers. And we use different normalization methods. We use different precisions, and we compare with the float 32-bit cosine computation as baseline. And we see that our methods are consistent. As we increase the precision of the binary representation, the matching quality improves. And then we also try to compare for a different data set to see if it's also consistent with different kind of data sets. So in table 3, we use Orbit data set along with the mini ImageNet data set. And we also see that our results are consistent. The matching quality is pretty good, even for 2 or 4 bits with the normalization method 2. And we see that compared to the baseline, our 8-bit implementation is pretty good with marginal improvements on 16 bits. So this is for the algorithm aspects. Next, we move on to the hardware side. So from the algorithm results, we realize that 8-bit implementation is kind of optimal for the trade-off with accuracy and hardware performance. So we implement 2-bit, 4-bit, and 8-bit in the hardware. And we measure latency, energy, and peak power. For hardware implementation, we use Jetson Xavier NX platform. And since these distance computations are mostly accumulation and some logic operations, these are not suitable for GPU or ML accelerators. It's more suited for CPU-based implementations. So we use 4 CPU-based kernel in the Jetson platform. We use PyTorch framework optimization for the cosine distance computation, which is our baseline. And then we use NumPy and Numba-based optimizations for our binary distance computation algorithm. And we see that till 4 bits, we get improvement both on latency and energy. However, for peak power, we see consistent improvements for all the bit precisions like 2, 4, and 8. That's on the bottom in the plot. And overall, we see about 2.5x power advantage from compared to the floating point baseline, mostly because we replace the logic operations with these binary computations. Finally, we try to understand if the existing hardwares are able to get the full benefits of our proposed algorithm. Even though we see that we are getting already 2.5x power improvements, still we see that with existing compute architecture and memory hierarchy, we are limited on getting the full benefits. That's why we looked into some advanced memory-based compute systems or in-memory compute. And for that, we use RM-based in-memory compute chip. This is what we got from Weebit, and this is a 130 nanometer technology node. And on the left side, the circuit diagram is mostly RM crossbar array, where we do the XOR operation for query vector and support vector. And in the middle, we show that the bitline current is inversely related to the Hamming distance. The higher the current, the better the match. And on the right side, you see the picture of the actual hardware. We have the RM-based in-memory compute chip that is interfaced with the microcontroller using a custom PCB. We can get external inputs to store on the RM, and then we can also get external inputs as the query vector, compute the matching on the RM chip, and then get the results out, verify those. At the same time, we can also measure latency and energy spent to do the matching. In the table, the first row is for this experiment, and we see that the search energy and inference time numbers, the search energy is in nanojoules, 1 or less, and the inference energy is in microseconds, which is already 1000x improvement over the CPU-based implementations. Then in the second row, we have some simulations for more advanced nodes for RM, and this is coming from literature for 40 nanometer and 28 nanometer RMs. And we see even a higher improvement there, and it's about 6000x improvement over the CPU-based implementations. Okay, so to summarize, we presented a binary distance computation framework to perform distance computations for few-shot learning using only accumulation and logic operations such as XOR or XNOR. We propose methods that leads to marginal loss in accuracy while providing savings in memory, energy, power, and latency compared to conventional methods. We also demonstrated successful realizations using RM-based in-memory compute to further improve the energy delay product in comparison to the embedded CPU-based realization. And finally, we showed projections for technology scaling for these in-memory compute platforms, where we could get about 6,000x energy delay product improvements. So that's all from me. Thank you, everyone, for your attention. I'll be happy to take questions, and I'll try my best to answer those. If I'm not able to do that, I'll follow up with the actual researchers from IIT Delhi and help you to connect offline. Thank you, everyone.
Any question from the audience? Probably someone has a question. Perfect. Okay, but thanks a lot. Thank you very much.
Thank you.
So then, welcome our next speaker, Renee. So really happy to welcome the next speaker. So we said already we will not introduce the speakers like biography. Probably you can introduce yourself like in the first 20 seconds. Really happy to have René here. So probably most of you knows René from his work on unsupervised learning, clustering, and many others. I'm really happy today to listen to his presentation about using Fisher transformers for positive estimation. So yeah, whenever you are ready. Oh, that's not correct. We need an adapter to the small size. Oh. Maybe you project yours. Just project yours. Just connect that like this. I have one. Yeah. This was good.
At least will work. You don't use this. Yeah. Yeah.
Fantastic. Yeah. So the floor is yours already. Welcome. Yeah.
Thank you very much. My name is René. I'm a professor at the University of Pennsylvania. Just moved from Johns Hopkins, and this is joint work with my student Kaliab Kinfu, who is at Johns Hopkins and also moving to Penn this coming semester. So when Nabil invited me, I told him, hey, I don't do anything embedded. That being said, the first topic of the workshop was on making methods efficient. And so this is exactly what this talk is going to be about. How do we make existing state-of-the-art post-estimation methods more efficient?
So human pose estimation has been one of those problems that has been around in computer vision for more than 50 years. And most methods are either 2D or 3D. 3D methods, naturally, you want to do a 3D reconstruction of the whole human body. While 2D methods, what you do typically is simply to try to detect 2D joints in the image and the video. And these are examples of state-of-the-art methods that are able to do extremely well, not only at detecting humans, but also at estimating the pose as they're doing very complex movements. There are many challenges in solving these type of problems. One of them is that the resolution of the images keeps increasing. And traditional methods, at least for the last 10 years or so, were based on using CNNs. And these methods work well on low and mid resolution images, but they don't work so well when you have very large resolution images. And the reason being that you really want to capture long range interactions between different regions of the image that correspond to different body parts. And when you have convolutions, they tend to be local, particularly for very high resolution images. So it is only natural that vision transformers have become kind of the method to go, because they are able to capture those long range interactions. The challenge, however, is that transformers are based on computing attention between every pair of tokens, so every patch in the image, if you wish, all pairs. And as a consequence, they suffer from quadratic computational complexity when being implemented. A third sort of orthogonal challenge is that transformers need a lot of training data to get them to work. And if you look at all of the databases that are available for pose estimation, they are not annotated equally. Different databases have different joints, so the annotation styles vary. And so this idea that I could just train a pose estimation method using all available data sets, it's not possible. So what we have been working on is on developing a method that we call EFI transpose, for efficient transformer for pose estimation. And the idea is really incredibly simple, which is rather than processing all patches in the image, just process a small number of them. And by doing so, we're able to dramatically reduce the computational complexity of transformers. But what is more important, right? Typically, when you become efficient, then you lose accuracy. So the good news is that we are not going to lose too much accuracy when we do so. And so the way we do so is by having good patch selection methods, right? If I'm going to throw away most of the patches in the image, well, what should I look at, right? It's not, I could look at random, but that's maybe not the best thing to do. So we're going to propose various patch selection methods. Is there an issue? Yeah. But that's okay. It's okay. So we are going to develop these methods to select a small number of patches. A trivial, very simple idea is, well, just use a simple network. Like maybe it's not going to be very accurate, but it's going to give you a guess of where the joints are. And now, rather than processing all patches in the image, just process those that have been selected by this lightweight selection network. The other approach is to actually learn tokens within the transformer that are specially dedicated to selecting the joints, and obviously to exploit the attention mechanism to be able to select those tokens. And as we're going to see, we're able to reduce the computational complexity of state-of-the-art methods from 30 to 44% approximately, with a minor drop of accuracy. In some cases, it's none. In some cases, we actually even do better. In some cases, we lose about 3.5% in accuracy. So before I get started, just let me tell you a little bit about the problem. So classical approaches, as I said, are all based on CNNs. And the way this problem is formulated is simply as follows. You begin with an image on the far left. You use a convolutional architecture that is an encoder that reduces the dimensionality to small dimension. So that's the encoder. And then the decoder goes back from low res to high res. Typically, for example, a UNet style architecture would be used. And the output, rather than being the 2D joints, which is how the data is annotated, is these so-called heat maps, where there is one heat map per joint. And therefore, what you do is predict that every pixel, what is the probability that it has joint number 1, joint number 2. Typically, there will be on the order of 20 something joints in the human body. So you have 20 such heat maps that are predicted as the output. And then you train them with a loss, which is based on the annotations of features or of joints for that image. All right. And here are the names of some of the most famous architectures that are CNN based for solving this problem. So transformers operate in a different manner. So you take the image, you divide them into patches, and now you compute attention between each and every pair of patches. And then you learn several representations based on these patches. And so the idea now is that you could try to predict from these patch tokens whether they correspond to a joint or not. Okay. And so that's the basic idea. So obviously, to do this, as I've said earlier, you need to compute attention between each and every pair of tokens. And there's been recent work showing that that's actually not needed, that by and large would make sense, right? Why should, in order to predict a particular joint, why should I be paying attention to the background? Right. Probably what I need to pay attention to is the relevant body parts that are needed for doing the computation. And so, but what are the relevant body parts? It's sort of chicken and egg, right? If I knew where the joints are, then I could figure out what to pay attention to, but that's a problem. So that's exactly what we're going to do. We're going to have a mechanism for selecting relevant patches that are able to therefore dramatically reduce the complexity and maintain accuracy. And so the overall architecture is essentially as follows. We're going to begin with the image. We're going to extract in principle all patches. But in addition, we're going to have these blue tokens that we called joint tokens, one per joint to be detected. And so both of them are going to be passed as an input to some vision transformer that now, the old vision transformers would only process the patch token. So I'm now increasing, if you wish, the complexity by adding these extra tokens that also need to be processed. But obviously, that's not what I want to do. So what we're going to do is to have internally some patch selection mechanism that is not going to process all of the patch tokens, but only a small fraction of them. And that's how we're going to gain computational efficiency. And then we are going to predict from the output of the transformer directly a heat map that does the reconstruction. This can be done again with a decoder that is a convolutional network, and that can be a lightweight decoder. And if you're really pressed by computation, rather than predicting these very rich heat maps, you can just directly predict the coordinates of the joints, which is what you're after. Typically, this isn't done because you lose accuracy by doing so. Using the heat maps is usually more accurate. But if you want flexibility, then you can use either of the two methods for doing the prediction. So the methods are actually incredibly trivial. At least the first two. We're going to propose 3 of them. The third one is a little bit more sophisticated. So the first one is simply take your favorite post-estimation network that is lightweight, that it takes the amount of time you're happy with. And then that's going to give you maybe the dark red regions in the image, in this skeleton. And then just select a few neighbors around those, because that light network might be wrong. So you might be selecting a patch that's not the one that actually has the joint. So the idea is select a factor of 3 or 4 more joints, which is still like 80 patches, as opposed to the million patches that are present in the image. And so that's kind of the red regions that you can see here. So whatever the lightweight told you plus 4 nearest neighbors. That's the first approach. Very simple. The second one is a little bit more sophisticated. The idea is from the joints, I have a guess of what the skeleton might look like. And so the limbs here are marked with blue. So now you can select patches along the limbs as opposed to just selecting along the joints. So it's slightly more complex, maybe a few hundred tokens that you need to process now. And the third one, and this is the one we really propose, if you wish, the first 2 are sort of baselines, is the one that is based on these joint tokens. And the idea is that these joint tokens are learnable, and they're going to be paying attention to each one of the patches in the image to select only a small fraction. So let me tell you the details of how we actually do that. So we begin with the red, which are the patch tokens, and the blues that are the join tokens. Then we do a computation of attention, and then we select the top K tokens with the highest attention. And then we refine both the tokens that are selected, but we don't completely forget about those that are neglected, but we refine them. And the reason is, again, because we can make mistakes, especially during the learning phase. We could be selecting the wrong one. So you want to compensate for those potential errors, at least during training. So the attention computation is really trivial. You just compute the attention between the join tokens, which is just 20 of them, and maybe the million patch tokens, which is a lot. But that's much farther, it's much less than a million times a million, right? It's just 20 times a million. And that gives you then the computation of the attention. Then given the attention, what we do is that we look at the attention coefficients in order to decide based on formulas that people have, because you have a lot of attention, you have multiple heads, so you want to integrate them into a single number that just gives you a single number for that patch. So there are formulas for doing those, and those are standard. People have proposed them in the past. The next one is simply to select the top K based on that computation of attention. And then we prune the attention matrix by selecting the subset of top K. And we update the tokens of one layer of the transformer only with the top K, okay? Then we refine also the non-selected patch tokens. Again, this is simply looking at the attention matrix of the non-selected ones, and we do a similar type of update. Okay, so this is all good. The issue is that there is one extra aspect. We need more data. Ideally, we would like to use more databases for training that we typically use. And the current approach is that you might train one transformer that is different on each data set. So how do we go around that? And again, the solution is incredibly simple, I have to say. You've got different annotations, one for each and every data set. What you can do trivially is simply take the union of all possible joints across all data sets. For each data set, you know whether the joint is present or not. So during training, all what you do is if the joint is present for that data set, then you use it in the loss. If the joint is not present, then you don't use it. And so effectively, you actually even learn how to train a post-estimation that is going to predict joints that were not annotated for that data set because they were annotated in a different way. Okay. All right, so we've evaluated a large number of methods, both CNN-based and transformer-based. And just to calibrate yourself at the very top, these are methods that are CNN-based. The last two here are transformer-based. Just to calibrate yourself, they have millions of parameters, between 1 million and 300 million. Some of our methods have 300 million parameters. But maybe the important number here is the flops that get to be used. So for light, HRNet is not much, but as you can see, you can get to the 20 giga flops there, right? So just calibration, this was the state of the art. And we've done it for 5 different data sets. Here there are 2 of them. So we train on COCO and MPI on the training set from those. And we evaluate on the validation set of those. But the last column, we didn't use for training. So the main observation before you get started is, in fact, that state-of-the-art methods don't generalize to other data sets, as I claimed, because the performance is much lower. Right here, we're in the 70s and 90s, and here the performance is at most 60. Okay. So how do our methods work on this data set? So this is the first one. So this is the efficient transpose method that I was talking about, with the baseline transformer, if you wish. So as you can see, we do significantly better in terms of accuracy. We go up from 60 to 93 on this new data set that we didn't have before. And for the others, we do better as well, right? Better in COCO, better than MPI, that all existing methods. But the flops it's okay, it's more or less comparable. It's not dramatically different, but it's still fairly high. Okay, so that's without using any of the methods that I've mentioned today, without doing any patch selection. We do better than the state of the art, and we do somewhat comparable in terms of computation with the baseline network, not the largest one. So what happens as we use the method? So the neighbors is selecting, a lightweight network, and then you select the 4 nearest neighbors. The skeleton is the one that selects patches along the limbs, and the autonomous is this method that automatically has these patch tokens. So sorry, the joint tokens to be able to do the selection. And so the key observation is that if we do patch selection, we lower the accuracy a little bit, but we do so with a gain of the order of 30 to 40% in terms of the flops that are used. Okay. And if you don't have any computational constraints, if you just want to do accurately, then you just use a larger network, the large transformer, and you're able to even do better. But you, of course, have a larger computational complexity. These are 3 data sets. Similar results can be obtained for other data sets, so I'm not going to bore you. The story is essentially the same. Maybe a different picture, a different way to see is, well, what if I have a mechanism to really reduce the number of patches, not just 4, I could use 4 nearest neighbor, 8 nearest neighbor. If I had a way to control based on the gigaflops, if I reduce in 1 gigaflop, how much do I reduce in accuracy? So compare, say, the red solid curve to the red dash curve. That is the MPI data set, okay? And the solid one is the method based on nearest neighbors, and the other one is the autonomous. Sorry, the other way around. And so what you can see is that for that data set in particular, the performance is relatively flat. It's like half a point drop in accuracy. So not a lot. For the green curve, that's the OC human data set. Then you see that the performance is really relatively flat, but eventually you drop, right? So this is 20 gigaflops on the far right, and you can go up to 14 gigaflops with just, half a point reduction in performance. And then the blue curve is COCO, that we do a little bit worse. If we go from 20 to 14 gigaflops, we lose about 1 point in accuracy. Okay. But as you can see, if you go below from 14 to 12, that's when you really begin dropping accuracy. All right. So to summarize, we've proposed 3 patch selection methods that greatly reduce the computational complexity of vision transformers. And the idea is super simple. Don't process all the patches in the image. Just process a fraction of them, select a few patches. And how can you do that? 2 of our approaches are simply run a lightweight network to select patches in the neighborhood of what the light network does. And the other one is train learnable tokens to do the selection for you automatically. The other contribution is, can we train transformers on multiple data sets simultaneously? And the solution was incredibly simple. Take all annotations, and for each data set, you're going to have only a subset of them, and just use the loss accordingly. And what we were able to show is that there is a substantial reduction in complexity with a minimal drop in accuracy. I guess I have 40 minutes, don't I? Yeah. Okay, so I have something else prepared for the remaining time. But let me just thank the work was supported by IARPA. I could entertain maybe a few questions about this before switching to the other, since the other is a very different topic.
Do you have any questions?
Hi, Renee. Thank you for the talk. As one of the organizers of the workshop, I would like to go back to your perhaps uncertainty whether your talk is relevant for this workshop. I think it's very relevant. I mean, look at the numbers, look at the efficiency improvements. And I think this, may be explained by something apparently Einstein said, that there's nothing more practical than a good theory. So yes, this is really good stuff for our workshop. Another thing I wanted to ask, as organizers, we have one of the gifts from NVIDIA for one of the invited talks. So I'm just curious, do you have a student who might be interested to implement something like this on an embedded vision platform that might help us decide where to send that gift?
So thank you for your comments and for saying this is highly relevant. I think my comments to Nabil were along the lines of embedded. And so I obviously, to be relevant to the workshop, it needs to be embedded. I do have, the student is really good and would be, I think he would be capable. I don't have research on embedded, so I'll be honest that if you ask me to do it, I think he will do it and we can do it. But it's not research that we usually do.
It will be an implementation for
Yes.
your work.
Yeah.
Thank you.
Just one short question for clarification. So this autonomous patch selection that you showed with joint token. So I couldn't quite understand it, but is it something that can be general purpose, like you can use it in any image, like you select patches from millions using some criteria, or is it something where you need annotation for annotated images to do this autonomous selection?
Well, in this particular case, maybe I should go to the general architecture. I think this picture would probably answer the question, right? In this particular case, the idea is you've got a transformer that has the patches as input as well as the learnable tokens. So once you look at the output after several layers of transformers, you are going to have the same sort of tokens, right? The patch tokens and the joint tokens. And for pose estimation, you have a loss that will compare, the token is going to be a vector of some dimension, right? You can have a regression to the location of in the image because you do have annotations. So in a certain way, for this task, you do have some sort of supervision that token number one corresponds to joint number one, and I know the location during training. And so, and the attention mechanism is this joint token is looking at which patches and trying to select a subset so that the features of that token are good for predicting location. So is this generalizable to any possible task that I just want to select a subset? Probably not, because the network has been trained to pay attention to the regions of the image that are relevant for predicting pose, in this case, for which I do have a loss. Are there potential modifications to this that would allow you to do that? Yes, provided that you can have a suitable loss for that purpose. At the other extreme, right, you've got architectures like the mask autoencoders that simply randomly throw away and they use reconstruction losses to do that. So are there possibilities that this could be modified? I think yes, but it will not be a plug and play. Yes.
Did you observe any differences in the conversions behavior of using the patch selection versus using attention between all patches?
I don't know the answer because it was implemented by, all the work is really Caleb. I would guess not, because he would have told me and we would have discussed it, but I don't know the answer to your question. All right. So let's see. Okay, the other topic, and I'll be brief, I guess I have 15 minutes or less.
You have 10 minutes.
10 minutes. Okay, I'll be quick as possible. It's very broad, and this is far less related to the workshop, but I think it's of very high importance today in the use of artificial intelligence to make it explainable. And this is important because methods are being deployed in society. We use them on a regular basis, and they can be adversarially attacked, or they might be in applications where it matters to come up with an explanation, such as medical diagnosis. Why did you predict that someone has Alzheimer? Well, probably you want to know that it's because certain region of an anatomical structure was maybe enlarged. So how do we figure out what's inside the black box? The way this is done today is by you look at the output of the network and you try to look, it's called post hoc explanation. And so you look at what was predicted and you try to understand what pixels in the image were relevant for that prediction. And the simplest approach is GradCam, where all what you do is you compute derivatives of the output relative to the input, and you look at large derivatives. The issue with that is that you end up with these heat maps, and now we just debate as to whether these regions make sense or don't make sense. So the good news is, well, we're happy with the performance of the network, so it's performing well, so we want to explain what it does. But the bad is that these explanations really, by and large, make no sense, or that, you know, at the end of the day, we're now trying to explain the explanations. Many people have been incredibly critical of the state of affairs. I'd like to read this quote from Zach Lipton at CMU, who says that the precarious state of interpretable deep learning is such that we should be far more scared upon hearing that a hospital or government deploys any such technique than upon hearing that they haven't. So what we argue is that rather than trying to do this post hoc, you need to do it by design. So you need to design a deep learning framework that is explainable by construction. The second is we need to agree, what do we mean by explainable? I mean, a lot of the research today is, this is my explanation method and these are my results. Usually, if you're mathematically principled, the first thing you do is you define what you mean, and then you compare methods against the same definition, as opposed to the method itself being the definition of what you're after. We humans like explanations in terms of words or patterns or symbols, or somehow the reasoning that led to that prediction. Explanations are not necessarily universal. If I was a clinician and I made a diagnosis, I would explain that to another clinician using some words, and I know the other person is an expert. But if I need to explain the same thing to the patient, I would use a slightly different vocabulary, a different way of explaining, because the patient is not a clinician. So even from the same data, the same prediction, the way in which I explain it depends on the user. Naturally, depends also on the task and on the domain, because the vocabulary might be different depending on what is it that I'm trying to explain. Even when I'm giving a talk, right, I would adjust to the audience, right? I would learn based on the question, oh, I did a terrible job, no one understood, so I will maybe try to explain it a little bit better, right? And so there is a little bit of interaction as well. So how could we make a definition and make this formal when it seems to be so esoteric and so dependent on the user? So the way we propose to do so is by having the user define what we call a query set, a set of questions, like the same thing as we give talks, right? If you don't understand something, you ask me a question. If I am a good explainer, you can ask me any question, I'll be able to respond there. Eventually, you will be satisfied. That's what we think explainable AI should be about, that the system should provide answers to any question the user might have, and the user will be satisfied, and that's when it's explained. And so what is an explanation? It's a sequence of questions and answers. And ideally, you stop after only a few of them, right? Because we don't want very long explanations, right? We want an explanation based on only a few sequence of questions and answers. So here is one example, and there could be many of them. Here, the task is to classify birds. I have no clue how that's done, but experts typically go through a sequence of several hundreds of questions. Here are a few examples. Is the shape perching like? Has a bill that is, the shape is all purpose? Is the belly yellow? Yes or no? And typically experts at classifying birds would be able to figure out the class with just a few. In this case, for this example, 7 questions and 7 answers, they're all binary. And you can tell and you can predict that it's a green jay with 99% probability. And in this case, there are 300 possible such questions. So you only select 7 out of those. So how could you make this mathematical? How is the process of selecting what question to ask, in what order, and to stop very quickly? So the strategy for doing this is old and well known. It's called InfoMax, or information maximization. And it's really inspired by how we play 20 questions with kids. I've played this with my 10-year-old. I told him, I have a number in my head from 1 to 10. Ask me a question. He's 10-year-old, and he, a few seconds, he said, is it less than 5? And I asked him, why did you ask me that question? Okay, he was not so sophisticated to tell me, but by and large, he gave me an answer to the extent that it's because it splits the space half and half. Right? And so that's what we do to be efficient. We try to come up with a question that divides the space half and half, and then we just need to analyze the other half. So that's exactly what this algorithm does. You select the first question. How is the question whose answer maximizes the mutual information with whatever you're trying to predict. So in this case would be, which one of the 300 questions about bird is the most predictive of the class Y? That first question, you've not seen the image. You have no data. It's like I just told you, guess a number between 1 and 10. You ask, is less than 5. You don't know the number, right? But you know how to ask the question. So that first question will be the same for the entire data set. The second question is the one that begins to be adapted. Depending on the answer to the first question, I'm going to select the second one based on the same criteria, maximizing the mutual information between the answer and the label, given the questions and answers thus far. And I stop when all remaining questions have no more information about what I'm trying to predict. Okay, to implement all of this, if I had time, I would spend a half an hour on telling you lots of deep generative models. You can do this with GANs or variational autoencoders. Right now, probably you'll do it with diffusion models. We come out with ways that you don't need to train generative models anymore. And certainly today we can do this with ChatGPT to generate the questions, and Clip to do the answers, and a gazillion other things that I don't have the time to explain you how we did. Example number 1, I'm running out of time, or? Okay. I have 1 minute, 2 or 3, or 5 minutes. Okay, so that's fine. Example number 1. So what we did here was exactly what I said. It's like we've got input data, images of birds, the set of 300 questions. It comes annotated with the answers in this case. And we learn a deep generative model that relates data, questions, answers, and the labels. Okay, and it's really trained. And once it's trained, you can compute mutual information. And so you can select the question that maximizes the mutual information. There are 200 bird classes, so I'm showing here only 10. And this is the run of the algorithm. So the first question that the algorithm asks is whether the shape is Pershing-like. And it would ask that question regardless of what the image is. And at the very beginning, it's roughly 1 over the number of classes. So it's very dark blue because all classes are equally likely. After you ask one question, the algorithm still doesn't know. But see, after just 3 or 4 questions, it has reduced the number of hypotheses to only 4 possible classes. After one more question, there are only 2 dominant possibilities. And in this case, it took no more than 7 questions or so to actually get that this was a great crested flycatcher with very high probability. Okay, so that's a running of the algorithm for that task. This is now for medical diagnosis. How do we do medical diagnosis today? You go to the doctor, they ask you questions. How do you feel about this? What the test could be the temperature. In this particular case, it's a data set where the data is the symptoms. So you have a sequence of symptoms. And so you ask one symptom at a time. And depending on that, you try to diagnose which disease it is. Okay, but it's the same process, and the questions are binary. We've tried this for many other tasks. This talk is a little bit old, but one other example we had was just text. So you can ask whether a certain word is present or not and try to classify the document. But at this point, what can this framework be used for? If you have a data set, if the user gives you the set of questions, if you have a mechanism to answer them, you just train these deep generative models to be able to compute mutual information, and then you have this information maximization to provide the explanation. Last but not least, and maybe I'm going to go back, the opening of the talk was, how do we make explainability by design? Why is this explainable by design? The reason it's explainable by design is because the algorithm predicts that this is a great crested flycatcher. Why is it a great crested? It's because it has these 6 attributes that are in green, and it does not have these 3 attributes that are in yellow. So there is an explanation attached with the prediction. In other words, you don't predict the class of the bird based on the raw pixels or deep features on the raw pixels, but the prediction is made exclusively based on whether the sequence of questions and answers that you've made thus far. Thank you very much.
Last questions. So we have 3 minutes.
It's a really interesting work, and we all know the post-hoc visualization has some drawbacks. And my question is your method need to answer all the sub-questions correctly to make final correct answers? And do you worry about if in such a framework, it will increase the difficulty of the whole task compared with end-to-end classification or end-to-end diagnosis?
So let's go with one question at a time. Do I need to answer all questions correctly?
Yes.
No. Basically, what happens is if some questions are, okay, there will be applications for which this would fail, and we have theory about that, right? If in the simplest example of guessing the number, if I make a mistake, then you went the wrong path and you can never come back.
Yes.
Right. So in many applications, though, that's not what happens. And what happens is that it'll take you more questions. Like if the questions are redundant, if there is some redundancy in the questions, eventually you can recover. And it's just that the length of the explanation is going to be longer. And so mathematically, the reason for that simply is the following. You are doing a computation based on maximizing mutual information. If all answers were correct, you are always going to select the most informative. If the answers are noisy, right? What is better is to select a good question for which there is a high probability that the answer is wrong, or to select a less good question that is very accurate. So that trade-off is automatically captured by selecting the most informative one, because mutual information depends on both the level of information of the noiseless answer as well as the corruption in this case. So typically, for data sets for which the query set is sufficiently good, and I don't have the time to explain what that means, although if you want to know, is there always needs to be questions that are close to being 50-50. Okay. If that's the case, then it'll just take you more questions to if you have an error. The other advantage, it allows you to diagnose the process, because you can now go back and intervene and say, if I flip the answer, would I get it right? Okay. What was your second question again?
So this is about if it will improve the difficulty compared with the end-to-end training.
The difficulty for
the whole mathematic framework of your like explainable network of your work.
Yeah. The first version of the paper, yes, because in addition to doing end-to-end trainings to learn the generative model, you need to now compute mutual information, which is typically costly and difficult. With the newer versions where we learn simply to predict what is the next question, we've been able to bypass. And so it's at this point is relatively equivalent to end-to-end training.
Thank you.
Thanks a lot. So thank you very much.
Okay, sure.
Okay, we are going to have a short break and we will start at 3:40.
No problem. Yeah. Come on. 可以说中文。那个要那个是吗？就是要接的那个啊。是用这个接啊，这个可以吗？我们就是这个而已啊。哦，不是这个。变成这个。其实可以直接从上学，不一定非要连，也可以啊，就是要连到这边给他们看。对啊，这个啊，啊，连 WiFi，对。
Hello. Hello, everyone. Welcome to the last session of the Embedded Vision workshop. In this session, we have 2 invited talks. And the title of the first invited talk is Exploring Bit-Level Patterns for Efficient NN Quantization and Deployment. And the speaker is Dr. Huanrui Yang. Huanrui Yang is a postdoctoral researcher in the EECS Department of US Berkeley and Berkeley AI Research, supervised by Professor Kurt Kuzer. His research interest lies in improving the efficiency and robustness of deep neural network models, with a particular focus on state-of-the-art model architecture and emerging hardware devices. Before joining Berkeley, Huanrui obtained a PhD in the Department of Electrical and Computer Engineering at Duke University under the supervision of Professor Heidi and Professor Yiran Chen. So let's welcome the speaker.
Thanks for the introduction. Thanks for the introduction, and thanks you guys for being here. So I'm Huanrui, and today I'm going to talk about some of my recent works on like bits level pattern exploration and also optimization for neural network models. So before I start, I want to acknowledge that all the work I'm going to talk about are contributed by my collaborators and advisors from UC Berkeley, Duke University, and also Nanjing University and Peking University in China. So I guess like for everyone sitting here, this the things on this page are quite familiar, and this is actually a very old illustration. I'm kind of using it throughout my PhD. Basically, what's going on to show here is like neural network models are getting larger and larger, and you see that in this figure, the largest ones are like this kind of 20 G-flops and maybe like 100 million parameters. But now you see that like for those large language models like Llama, we easily get to billions of parameters. So it's getting larger and larger. And the growth of model sizes are kind of beyond the speed of growing of the hardware that are supporting those. So for the kind of real application of deep learning, especially on edge devices and embedded devices, we do need to compress the neural network model so that it can fit into the limited computing capability, memory, and battery energy on those devices. So there are a lot of model compression techniques actually, but for today's talk, I do want to focus on one thing that's kind of on the bits level. So no matter how the models are designed or like how the weights are, everything on the device are stored in bits for most of the time. So here that's like for general hardware like GPUs or CPUs, a lot of them are using floating point representations where like the most common one is 32 bits, and also recent developments in NVIDIA GPU also supports like 16 bits or 8 bits floating point. So floating point is pretty good at representing the numbers accurately, especially for numbers with a large dynamic range. But for from the efficiency side, like if we really want to have inference with the model for a low cost and a fast speed, then on embedded device and specialized hardwares, most of the time people want to use fixed points instead of floating points. So for fixed point device, it takes much fewer computation cost, and also the fixed points algorithm units take less energy and less area on the chip compared to a floating point with the same procedure. So in a lot of like previous efficiency efforts, most of them are focusing on like model architecture, such as neural architecture search or pruning. And also there are some work focusing on like how to convert the data from a kind of floating point into a fixed point. Like most of the quantization work, working on like determining quantization precision or determining the quantizer for the conversion. But what I want to point out here is that there haven't been a lot of efforts really on exploring and utilizing the exact bit level pattern for our model being deployed on the hardware. And this would be the focus of this talk. So as a brief introduction for the overall roadmap, to start with, I want to first introduce our work in SARR 2021 about inspire to develop a mixed precision quantization scheme with the bit level sparsity. So we basically propose a training framework that can train the model in the bit level and use that bit level optimization to finally develop a mixed precision quantized model. Then starting from that work, the next thing I'm going to talk about is a work we were going to present in this year's Design Automation Conference on improving this bit level optimization with a smooth continuous specification approach. Then finally, kind of utilizing these previous algorithms on controlling bit level patterns, we finally showcase a potential usage of this kind of optimization on the specific hardware of a rerun-based neural network accelerator, where we perform a architectural bits pattern co-design to achieve a efficient neural network deployment and inference. Yeah, so let's dive into the first topic. For quantization, actually, it shares a lot of similarity with other model compression techniques like pruning or factorization. So the most important point is that all of these methods can utilize the difference in the layer importance. So in neural network, some layers are always more important than the other layers. So in the case of compression, we may want to compress those less important layers more and kind of keep the more important layers so that in the end, we have a better trade-off between the model size and the final performance. Then for the case of quantization, this leads to a mixed precision quantization, where we want to assign a higher precision to the important layers and lower precision to the less important layers. Then the key problems comes on finding the optimal mixed precision quantization scheme. So what exact precision we assign to each layer in the model. The key difference between quantization, or also it's the key challenge for quantization, it's that precision itself is not a differentiable function with respect to the weights of the model. So when we do pruning or factorization, we can say that's the sparsity of the weights or the rank of the weight. This can be represented as a function of the weight value. But precision is independent of weight value. Given a weight value, you can represent it in any precision. So this means that we cannot directly represent or compute a precision of a weight value or of a weight from its own value. So we cannot optimize it. And previous methods on mixed precision quantization utilize some searching technique, or just use some static importance evaluation on determining the which layer is more important and which layer is less. But this whole process of designing this mixed precision quantization scheme often takes a lot of cost and may not reach the real optimal solution. So in my work, our goal is that we want to achieve a dynamic precision adjustment with a differentiable regulator so that during the training of a neural network model, we can directly end up with a optimal mixed precision quantization design. And as I mentioned before, that precision is not a function of weight value. So we cannot just look at the level of the weight. We need to go deeper into the bit level to see whether we can find anything that can represent precision at that level. So let's take a bit level of quantization, or of the quantized weight values. So suppose we have a fixed point quantized matrix. Here, I'm showcasing kind of a 4-bit quantization. So the question is when can we change its precision? Then we see that there are 2 cases that we can actually reduce its precision. The first case is that it's kind of called a underflowing. So all the numbers within this matrix are not utilizing the most significant bit. So all the most significant bits are 0. Then we can just remove that bit with no cost and no change to the value and reducing the model precision. The second case is that the least significant bits of all elements are 0. Then we can just simply shift everything to the right by 1 bit and reduce its precision while multiplying a scaling factor of 2 to the whole matrix. So in those cases, we see that by observing the bit level pattern, we can actually determine like whether the precision of this matrix can be adjusted. So this inspires us that if we can just always train the model in this bit level representation and observing how those bits are behaving, then when we find a so-called structural bit level sparsity, where a certain bit of all the elements in the matrix is 0, then we can just remove that bit and reduce the precision of that layer. And that leads to our method, so-called BSQ, or structural bit level sparsity quantization. And we can use that to train the model into mixed precision. So here are some like more technical details of these methods. Like the first thing we need to resolve is how to exactly train a neural network in a bit representation. To do this, we follow the typical design of quantization-aware training, where we utilize a dynamic range scaling. And we start the model with 8 bits, as most of the models can keep their original accuracy under 8-bit quantization. Then instead of directly optimizing this quantized weight, we convert it into binary format and consider each individual bit of this quantized weight as an independent trainable parameter. And to make this training work, we utilize the idea of zero-zero estimator, where we have accumulate the gradient in the floating points for each bit. But for the forward pass and loss computation, we round it into the exact binary form. And since each bits are now kind of allowed to take floating points, we actually allow them to take any value between 0 and 2, so that it can both overflow and underflow to adjust the precision. Then to induce this bit level sparsity we desire, we apply the commonly used group lasso regularization on the bit level trainable variables, so that we group the a certain bit of all the elements in each layer. And with this regularizer, it will either be all 0 or all non-zero, so that we can decide whether to remove or retain that bit. For the overall training objective, we have apply a strength to this regularization, so that it reflects how much, like how many bits each layer are contributing to the entire model size, so that the larger layer will be penalized more. And this leads to a kind of better efficiency accuracy trade-off in the end. During the training process, since we want to dynamically adjust the precision of the layer and reach a mixed precision quantization in the end, we perform a periodic requantization and precision adjustment, so that in the requantization step, we convert each bit to exact binary value and remove the all 0 bits to decrease the precision. And since like we allow each bit to take a value between 0 and 2, so it's likely that the most significant bits may overflow. Then in the case of an overflow occur, we just increase the precision by 1 bit, so that this the whole thing will fit into the current quantization scheme. With this kind of training process, we find that we achieve very good performance actually. So the first thing we observe is that as we change the overall regularization strength, by increasing the regularization strength, we find that our method are assigning fewer bits to each layer throughout the model, and we are achieving kind of a larger compression rates with the cost of some accuracy drop, which means that we can effectively control this trade-off between model size and performance with a single hyperparameter of the regularization strength. And then we also observe kind of compare our BSQ method with directly training the model quantized to the same precision from scratch. And this actually echoes what Jose presented earlier in today's workshop, like train big and inference small. So we find that by starting the model training with a higher precision and gradually adjust this precision during the training process, we achieve higher performance than just simply training this kind of lower bits model from scratch. And for experiment results, comparing to some of the concurrence methods at that time, we find that our method can achieve larger compression rates under a similar accuracy. And we tested our method both on Cvpr and ImageNet, and it's working well in both cases. So this results looks pretty good from the first look, but during our experiments, we do see that there are still some drawbacks with our method. And that leads to our second work on trying to improve the stability of the BSQ method with a smooth optimization method, which we call a CSQ, or continuous sparsification quantization. So for limitations of BSQ, we find that first of all, in our experiments, we do find this training process to be unstable. Like when we do repeated experiments, we will see some variance between for each run, what's the final model size will end up and what's the final accuracy will be. And we analyze this instability and find the key reason are related to the use of series-through estimator and the requantization process. So the ST used introduce a noise in gradient calculation because we are estimating the gradient of fixed point weight with a floating point alternative. So there's a noise here, and as we are training with each individual bit, this noise actually got intensified and leading to a unstable training process. And also we find that the requantization and precision adjustments of BSQ are interrupting the training dynamics, where each time we requantize, all the weight values are changing. So in that case, some of the momentum stuff needs to be recalculated, and it's causing some troubles in the convergence. So this hints us that to resolve this issue, we need to relax this binary bits value and also the binary bits selection to improve the stability. And also, we also find there are potential some problem with the efficiency of the training. So although the model we end up, like the mixed precision quantized model, is efficient, this whole training process isn't that efficient. So first of all, as I mentioned, we can tune this trade-off between model size and accuracy with the regularization strength. We cannot really tell, if we just want the model to be 4 bits, how large regularization we need to apply. This is one issue. So we need a lot of trials and errors to find the suitable regularization strengths to use. And also for another inefficiency is also from the requantization, where when we do requantization, actually the bits value will be affected by neighboring bits. Like if we say we have this 1.75 as some bits and 2 zeros afterwards, seems like we only have 1 bit here, like 1 non-zero bit. But when we really do the quantization, actually all the bits are 1 in this case. So this means that the sparsity we achieve during the training process isn't that stable and isn't that meaningful. So during the requantization, a lot of sparsity may be lost. So this also hints us that we should have a independent control of the bit selection and bit value so that we can know exactly which bits we are using in the end. So to resolve these 2 issues, we propose to look at some more advanced optimization techniques. And here we utilize the technique so-called continuous sparsification, which is proposed actually in the model pruning field. The motivation behind here is that actually we only need the exact binary values at the end of the training. So during the training process, we can have them as continuous values. And actually we desire all those bits as continuous values so that we can compute the gradients smoothly. And continuous sparsification actually is designed just for this motivation, where it's relaxed the binary value into a sigmoid function. And the sigmoid function here has a temperature beta, where when the beta is smaller, this function behaves more like a sigmoid, and it's smooth and with a very accurately defined gradients. And as we increase the temperature beta throughout the optimization process, this sigmoid function will get steeper and steeper. And in the end, when we have a very large beta, the output of this sigmoid is almost binary. So at that time, we can get the exact binary values in the end. Specifically for our case, like for the case of bit level training, there are 2 levels of sparsifications, or like 2 levels of bits of binary stuff that can be relaxed with the continuous sparsification. The first level is on the bit level 0 estimator, where instead of relying on this rounding function, we directly consider the bit value of each bit as a continuous sparsification function. So here, this mask, either MP or MN, is a kind of a weight of the bit value, where it can take any floating point value between -infinity and +infinity. Then after converting by this sigmoid function, it becomes a sort of a relaxed binary value between 0 and 1. And the second level of the continuous sparsification that can be applied is on the selecting of the bit. So as we mentioned, we want to make an independent control of bit value and bit selection. So for bit selection, we introduced an independent bit mask, which is also controlled by a continuous sparsification variable. Then in the training time, to make an exact selection of the bits, we also have multiply this QB term, which is a binary value that's being sampled from a Bernoulli distribution of the bit mask in each layer. So that in each step of the training, we are always using an exact number of bits rather than something like half a bit or something, which is like not very useful for calculating the overall sparsity. So with this adding the continuous sparsification into the overall framework, this allows us to control the model precision independently of the weight values, and we can regulate the growing and shrinking of the model precision of each layer by using a L1 regularization directly on the bit mask of each layer. And here, like to allow a accurate control on the final model sizes we achieve, we introduced the idea of having a dynamic regularization strength determined by a budget scaling delta S term, where this delta S is defined as the difference between the current model size and the desired model size. So in this case, if the current model size is larger, then delta S here is positive and maybe large, so that it will enforce a strong regularization on the bit mask to make it even sparser. But if the model end up having a smaller model size compared to the budget, then this delta S term will become negative. So instead of penalizing the model, it will actually encouraging the model to use more bits, so that this will allow a growing of the precision in some layers. And this leads to the overall SSQ training algorithm, where we start by joint optimizing both the bit values and the bit mask with this continuous sparsification relaxation. And throughout the training process, we exponentially grow the sigmoid temperature, kind of starting from 1 all the way to something like 300 or 500, which will lead to an exact binary value for all the trainable parameters in the end. And finally, we can just directly output this mixed precision quantization model we achieve. Or we can also perform a additional fine-tuning where we fix the bit mask, like we fix the bit selection and fine-tune the bit value of each weight, each of the entire model by doing a rewinding of the bit value temperature so that it will be relaxed back to a continuous value, and throughout the fine-tuning process end up with a new binary value in the end. Yeah, from like after we apply all this in the experiment results, we find that first of all, this utilization of continuous specification gives us a significant performance boost comparing to the 3-through estimator scheme previously. So here on this page, we just compare like under the case of uniform quantization, like how is the bit level continuous specification comparing to just using the traditional 3-through estimator based quantization we are training. And we find that under all the procedures, we are achieving like more than 3 or 4% accuracy gain comparing to just doing the quantization we are training in the traditional way. And by further introducing this bit mask and allow the model to grow into a mixed precision quantization, this performance can be further improved by about 1% comparing to the uniform quantization scenario. And here we show that our proposed budget-aware model size regularization is also working as desired, where like when we are changing this base regularization strength, as long as it's within a reasonable range, then throughout the training process, this kind of our regularization always control the overall model size to be close to the desired model size, which is represented as the red star. And in the end, the model will converge into a size that's very close to our budget. For comparing with other method, we find that CSQ is leading to a better accuracy model size trade-off comparing to BSQ. And we find that the final compression rates of the model are always complying with the budget we set, which is represented as this T here, where like T1 means we are targeting a average 1 bit and T2 targeting an average of 2 bits, something like this. And we find that the CSQ is especially effective on ImageNet model, which kind of shows that this better stability achieved with this continuous specification actually helps the performance on those large scale models. And we are kind of confident that CSQ will be more suitable to be applied on like those even larger models, such as the large language models that are emerging in recent days. Yeah, finally, actually I'm talking a little bit quick, but yeah, finally, let's look at the rerun, like how are we going to utilize this kind of bits patterns we observe in a real hardware scenario, like how this co-design between the bits pattern and the hardware can lead to a better overall performance. So I see that one of the previous talk I already mentioned ReRAM, but in case you here are not familiar with ReRAM, ReRAM is actually a in-memory computing device. It's a like emerging hardware devices that are really good at computing matrix multiplications. So the way ReRAM works is that kind of given this crossbar, we put the weight of a layer, or like puts the weight of a linear layer as the conductance at each crossing point of the crossbar, and apply the input activation as a voltage at the weight lines. So that with the physical laws, each bit line will actually end up to be the computation results of the vector multiplication of all the input activation and all the weight values. So if we just read out the current going down this bit line, we can directly get this vector by vector multiplication results. And if we can read out the bit line of read out the current of all the bit lines, this directly gave us this full output activation, where like have the computed after passing the inputs through these layers. So this kind of architecture enables us to do this kind of matrix multiplication all in a single cycle. And theoretically, like if you can build a ReRAM crossbar with that's very large, then it can just compute a extremely large matrix multiplication in a single cycle, which sounds very promising. And that's why a lot of work are saying that ReRAM could be the kind of the foundation of next generation of in-memory computing hardware. But the reality is, like in practical ReRAM based accelerators, we cannot really have a crossbar that's infinitely large. And even if like we can build the crossbar to be large, the computation can only be performed in a so-called operation unit based operation unit, which only contains limited amounts of word lines and bit lines, such as in the kind of the data in 2019, where the maximum operation unit size can only be like 9 bit lines and 8 bit lines. The reason behind this is that if we are activating too many bit lines, then the current along the bit line will be too large that it will lead to a significant IR drop and conductance variance in the final accumulation, which makes the computation inaccurate. And if we are having too many bit lines, because we need to kind of calculate the current on each bit line, then we need a lot of analog digital converters under each bit line, which is very area consuming. So that's why that's both the bit line and bit line in a crossbar, it's limited in the real world accelerator design. And then, so in this case, like, although there are a lot of neural network compression works that are trying to accelerate for a ReRAM based hardware, they do not really consider this practical constraint on the ReRAM device. Therefore, in reality, ending up in lower model compression ratio and lower speed up. And in our work BWQ, we propose a hardware software co-design idea which considers this parallelism constraint on ReRAM based accelerators. The way we do this is that instead of just quantizing the model in a layer-wise fashion, we do the quantization in a more fine-grained fashion of a block-wise mixed precision quantization, where we just allow the precision of each weight block that has the same size of the operation units to be different. And to do this, actually, this can be, we can directly use what bit level training algorithms we proposed previously to achieve this kind of mixed precision quantization. The only thing needs to be changed is like how are we grouping this regularization. And this kind of new fine-grained mixed precision quantization, we find that the proposed BWQ, it's kind of ending up with a weight matrix that each block are having a different precision. And this is allowing a much higher model compression rate comparing to like just having a layer-wise mixed precision quantization. Then, like with this kind of software or the model architecture, we can further design a hardware accelerator, which we call a BWQH, that can efficiently support our block-wise mixed precision model. And in this case, we propose 2 techniques. One is to kind of having a precision-aware deployment where we have we put the weight of, we put each bit of the weight into a single crossbar so that it can utilize the full occupancy of the entire crossbar. And also we kind of do a mapping of the crossbar onto the ReRAM device so that during the inference time, if there's a fully sparse crossbar, we can directly skip its computation so that overall all the cycles are utilized for the computation process. Yeah, finally, our co-designed architecture achieves a average speed up over the baseline for like 7 times and a average energy efficiency for almost 21 times. And we find that this, like all the techniques we propose, like the weight compression, activation compression, and this co-design hardware are all contributing to the overall compression rates we achieve in the end. Yeah, so in conclusion, in this talk, I introduced 3 works where the first work, BSQ, introduced the idea of viewing precision reduction as a bit level structural pruning and introduce the mixed precision quantization with bit level group lasso. Then CSQ further improved the stability of this bit level training with the continuous specification technique and achieves a independent precision control, enabling the budget-aware regularization. And finally, this co-design work, BWQ, shows that co-designing this bit level and architecture pipeline for emerging device can lead to a better efficiency. So in the end, the final takeaway word would be that exploring bit level patterns can help on designing better and more efficient neural network models on target hardware. And this is something I want to advocate to the field to look further into. So finally, before I go, just a quick advertisement on some recent work on model compression. So in this year's Cvpr, we are presenting two works, one on vision transformer pruning and the other on vision transformer quantization. So both of them are on Thursday morning. So welcome to check out our posters. And also, as the emergence of diffusion model, we have a recent work of Q diffusion by performing post-training quantization on diffusion models and achieving like 4-bit model without losing much performance. So we have the all the code and the model on this project page, and also welcome to check it out. Yeah, that's all of my presentation. Thanks.
Thank you very much. Any questions?
Yes. So do you see your work on resistive memory leading to new architectures, new processors, new ideas in that direction?
Yes. So actually, like first of all, this work, the BWQ, is already a hardware software co-design work where we are kind of both designing the neural architecture and also the architecture on the hardware or the data pipeline on the hardware to fully utilize the benefits of the model compression. Yeah, and also like specifically for VRAM, actually VRAM is a very good device. Like it has a very high promise with those computing memory characteristic and low energy consumption. But there are a lot of real constraints of it. And a lot of those constraints are actually on the bit level, like not only on those kind of baseline sizes, but also on how many bits you can put into the crossbar or something like this. So I believe that with more of this kind of investigation into the bit level pattern, we can actually design better algorithm that can be accelerated by those emerging memory devices, and which will lead to a like higher energy, higher efficiency and faster inference compared to the current conventional accelerator architecture.
Any other questions?
Thanks for the talk. Really interesting. I'm just curious about, say, like normalization of data and everything. Like, you know, with normal nets, we'll sort of, you know, normalize it in a certain way. Like, do you need to do any sort of like different processing, like when you're sort of moving towards, you know, like quantizing on, say, like 8-bit schemes?
Yeah. That's actually a very good question. So actually, it depends. So like for some modules like batch norm, actually they can be absorbed into the weight before the quantization or before the deployment. So it can be dealt together with the weights. But for some other architectures like layer norm, it would be harder to kind of just squeeze it into the weights, and you need to deal with it specifically. So traditionally, like we just consider those normalization layers as very kind of low cost layers, so that we are able to just keep them as floating points, and like we just do a conversion between quantize and floating points when we reach those binary layers. But recently, there are also some research showing that for specialized hardware, like especially for those edge devices, this conversion between binary and floating point is a bottleneck. So there are some work that are working on like fully integer compression for the entire model, including those normalization layers. So like for work within our group at Berkeley, there are so-called HAWQ v3 and iBERT, which are dealing with this fully integer inference and model compression. So if you are interested, you can also check those out.
Thank you. Next question. I have questions.
Okay.
Okay. So you said that you have a paper which is about post-training activation quantization for transformers. And my question is, can the methods that you introduced just for for CNN be applied to vision transformers? And can quantization aware training methods be applied to vision transformers?
Yes, that's a very good question. So I think first of all, the answer is definitely yes. So because like all the techniques we propose are not for any specific architecture. So as long as it can be trained differentiably, then we can use our methods. But one specific issue is vision transformer or like all those emerging architecture like diffusion models is that there are some very special architectural components in it, like maybe the GLU activation or the of the attention units, or like in diffusion, they have those UNet architecture. So those specialized architecture are leading to some non-standard distribution in like activation or the weight values. So that this may lead to some challenges in applying quantization. And actually, like for both this noisy quant work and Q diffusion work, we are looking into this activation and weight distribution and are proposing some specialized techniques that are more suitable for this specific architecture. Yeah.
Thank you very much. Let's thank the speaker again. So the title of the next invited talk is Perception-Inspired Video Coding. And the speaker is Professor Mai Shi, but Mai Shi cannot attend Cvpr. So Dr. Lai Zhang will make a presentation. Lai Zhang is a postdoctoral researcher in the Computer Science Department of University of British Columbia, supervised by Professor Leonid Sijo. His research interests include low-level vision, medical imaging, and video compression. Before joining University of British Columbia, he obtained his PhD degree from the Electric Engineering Department, Beihang University, under the supervision of Professor Mai Shi. He received multiple awards, such as Outstanding Doctoral Dissertation Award of China Society of Image and Graphic, winner awards of Cvpr, NTIRE 2022, and ECCV RVC 2022. Yeah, so let's welcome Dr. Lai Zhang.
Yeah. Really?
Please share your screen again.
Oh, that's shame. So, how can I do? I'm going to share the desktop too, right? And move it to here. Sorry. I think I will
Okay, move it
move
back.
back at the moment. Please.
Maybe you can move it back and
Yes. Yeah. And yes. It's not right.
Okay, yeah, perfect.
Perfect, right? Okay, thank you. Thank you for your introduction. And I'm Lai Jiang. It's my honor to be here. And currently, I'm a postdoc in the University of British Columbia. And Professor Mai Xu was my PhD supervisor. And I'm going to go back to Beihang University next year as a faculty of the Professor Mai Xu's group. So for some reasons, I'm on behalf of Mai to have this talk today. And I'm familiar with some works in these slides, and I will try my best to introduce them, but probably not as good as Mai does. So I apologize in advance. So our topic for today is the perception-inspired video coding. And the talk will be divided into these 4 parts: the background, the data-driven video saliency detection, the perception-inspired video coding, and the perception-inspired omnidirectional video coding. And here is the story and the background. There are the pictures of the making New Year wishes. The above one is taken in 2005, and the below one is taken in 2013 at the same place. We can obviously find that as the smartphones are popularly used, we generate the huge amount of images or videos every second. However, it's a challenge to store or deliver this huge amount of the images or videos, especially for the embedded system. And on the other hand, as we know, big data is one of the key factors to boost the development of deep learning. And establishing a large data set is really important for training the advanced architectures. So here are some statistics. There were around 1.2 trillion images taken worldwide in 2017. And according to the Cisco Visual Networking Index, the video data grows from 504 EB in 2016 to 1910 EB in 2021. Besides, the growth rates of the global mobile data is around 47% each year. So the huge visual data becomes a big challenge for visual communication since the bandwidth is limited. Similar to the embedded systems, the computational resources are also limited. So how deliver or process a huge amount of high quality videos is an urgent need to significantly improving the coding efficiencies of video compression. The coding efficiencies means the read distortion performance. That is like we want to obtain a higher quality of the compressed videos at the same bit rates, or we want to have a nice bit rates at the same visual quality. And we can see from this figure that the coding efficiency develops along with time and benefiting from the advanced video codecs. But the coding complexity also increased, and this course is extremely heavy for the current video coding standards. But the improvement gain of the coding efficiencies becomes smaller and smaller. It's kind of a border effect. However, we can find some breakthrough of the video compression from our human visual systems. According to the research of our brain systems, we have more than 1 billion rods or comb cells in our eyes or in our retina. And it's like 20 super high resolution cameras with around 1.4 trillion BPS video stream. In contrast, the number of V1 cells between our eyes and brains is around 1,000, similar to 8 million BPS bandwidth. That huge compression efficiencies is mainly due to our human visual systems. In the human visual systems, the viewport of our eyes is more than 90 degrees, but the region that clearly seen by our eyes with high resolution is only 2 or 3 degrees. That means the videos exist a very large perceptual redundancy. So we can learn from the human and reduce the perceptual redundancies in the videos. So based on the human intelligence, some approaches were proposed for video compression. For how to explore the procedural redundancy, we developed video silencer detection methods. And for how to reduce perceptual redundancies, we proposed the perceptual inspired video compression methods. And finally, we extend these methods to the omnidirectional videos and develop the perception inspired panoramic video coding methods. Yeah, here is a deep learning based approach for the video silencer detections. We collect really large scale videos from diverse content and conduct the eye tracking experiments to record the human fixations when they viewing these videos. And we conduct analysis on the recorded eye tracking data to find some potential patterns of video silency. And based on the analysis, we design the handicraft features for video silency. We also develop the deep neural networks to model the video silency. Here is the eye tracking database. We have established like 3 databases with eye tracking data. It's about over 2,000 videos and with more than 8 million of fixations from over 30 subjects. And you can see that the heat maps are the fixations when the subjects viewing these videos. And here is one of our analysis. Taking this video as examples, we can see that at the beginning, the human attention is equally attracted by these two penguins, and but that means the regions with the object can always draw a majority of the human attention. But after that, when this big penguin suddenly fails, the visual attention changes to the big penguin from this small penguin. So that means the human attention is more likely to be attracted by a moving objects of the moving parts of objects. There's some statistics. We found that around half of the human attention focus on the regions that with top 10% motion intensities. And based on the data analysis, we developed our 2-branch convolutional neural network structures for extracting the intraframe spatial attention. Basically, we have a objectness network and a motion subnetwork. The objectness subnet is used to extract the features related to object and is pre-trained by our existing object detection backbone. And similarly, the motion subnet is based on a pre-trained optical flow detection backbone. And we use the features from the objective network, subnetwork, and the motion subnetwork to concat together and to generate a silence map that can reflect the intraframe silency. And as we can see from this figure that during training, we can see the network will focus more on the moving part of the object, like the wheels of this car. It's also what the ground truth silency tells us. And after that, with given the features from our convolutional neural network, we also propose a convolutional LSTM structure to generate the interframe silency. The features from the CNN are then input to this 2-layer convolutional LSTM. And based on the traditional LSTM, we design a sentence bias dropout denoted as the Z over here to improve the generalization ability of the network. In this way, we can incorporating the prior of the sentence bias of the silency. And then we also developed a sparsity weighted loss in our convolutional LSTM, and the insight of it is to encourage our network to predict the silencing map as sparse as the ground truth. And we measure the KL divergences between the intensity histograms between the predict and the ground truth stance maps. In this way, we can have the sparsity priors of the human attention. This is the objective results of this work, and we can see that in all three metrics, the EUC, NSS, CC, and KL, we outperform the sorter. And this is a kind of application studies like to verify the contribution of each components. And here are some subjective results we can see compared with the other methods, our silence map is more close to the ground truth. Here are some published works of Professor Mai Xu on this area, on this topic. And the second is the perception-inspired video compression method. And the goal is to obtain the better rate distortion optimization performance, benefiting from the human perception. It includes two parts, that is the quality optimization, which can be regarded as processing during the video coding. And another part is quality enhancement. It can be regarded as poster processing after we have the compressed video frames. And specifically, we propose a perceptual rate control method for HUEC video coding. And we propose a multi-frame quality enhancement for the compressed videos. The background of this two work is that at that time, there are few works on closed form rate distortion optimization on either objective or perceptual quality. And there are few works adopting multi-frame approaches on video quality enhancement. Yes, the traditional rate distortion is mainly based on the MSE distance between a reference frame and coded frames. It's an optimization function, and in our method, we have some improvement to propose rate perceptual distortion optimizing models by considering the predict silency. And here is the pipeline of the optimization model. We embedded the silency detection into our existing bit allocation method in EVC. And basically, given the bit target bit range, the bit allocation method need to output QP maps, that is kind of bit allocation maps, which tells us which pixels we need to pay more bit rates and which pixels we don't need to pay many bit rates. And this is the lambda function that's used to build the relationship between the BPP, the bit per pixel, to the final QP output. And it's a kind of experimental function with that. And the I index indicates that each coding unit of the input frame. And the alpha and the beta are the unknown variable, but we can upchange during the coding. Yeah, recall that this is our optimization functions. We need to minimize the distortion of each coding unit and let the final overall bit rates less than target bit rates. And after applying Lagrange multiplier and let the derivative and let the overall bit rate equal to R, and let the derivative to be 0, we can finally obtain two expressions. Of one is for the bit rate of each coding unit, and another is overall expressions of the bit rates. And based on these two equations, we need to optimize the lambda, and after we optimize and after we obtain the lambda, we can calculate the bit rates of each coding unit. So After that, we do some simplifying on these two equations by replace some items by the new notation here. The R tile and the lambda tile and the BI. So when we simplify the equation like that, we then conduct the Taylor expansions on this equation to like this, and we just keep the first three items of the Taylor expansion. We can see that all these items are not related to the lambda, so we can regard it as a cubic equation to solve the lambda. Assume that the lambda hat is the answer of this cubic, is solution of this cubic equations. We can see that this lambda hat is more accurate than the original notation of the lambda tail. So we can use this lambda hat to replace the lambda tail over here and make this is all processes iterative. So after many iterations, we can obtain the more and more accurate lambda as after it is coveraged. We can finally obtain the lambda and calculate all the bit rates during the video coding. And our experiments show that the convergence speed is really high, and we can see that the errors will be very light only after 2 iterations. And this is some subjective qualities of this method. And this one is a perceptual heat map obtained from is a ground truth perception heat map. And this one is original HEVC codec, and this one is of our method implemented on the HEVC. We can see that for some key regions like the face, the eye, the mouth, our methods will be more clear, even in the same bit rates. This is the bit rates this quality is obtained from actually the background. We can see the background is smoother than the original HEVC. That's because we allocate less bit rates to the background and put more bit rates to the regions we think they are consistent with the human vision. And finally, the coding efficiencies is almost twice compared with the traditional HEVC codecs. And after that, another work is the multi-frame quality enhancement for the compressed videos. The motivation of this work is that the high quality, there exists high quality neighboring frames may help to enhance the low quality frames. From the figure, we find that there exists large quality fluctuations between the frames. That means there are some frames with very low quality, like the frame number 60. The PSNR is like 24 dB, but the neighboring frames is with really high quality. It's like 27 dB. So the motivation of our work is to use this as high quality frames to enhance this low quality frames. First, we apply our existing peak quality frame detector, which is built on a pre-trained SVM. And then we develop some neural networks. It includes motion compensation networks that learn to align the peak quality frames to the rest of the frames and concatenate them together to input to another quality enhancement network subnet. And based on the peak quality frames and the low quality frames, we can finally improve the video quality over all video frames. And here are some results of it. Averagely, we can improve the PSNR like 1.5 dB, and this is relative higher than all the existing methods. This is some subjective qualities. We can see that in our method, we works pretty well on enhance some detailed objects inside the video frames, like the basketball or this is mouse. And here are some published work of Professor Mai Xu on this topic. And the last part is the perception-inspired omnidirectional video coding. And we know the omnidirectional videos are more challenging because it has a higher resolution, and the human perceptual behaviors is different between the omnidirectional videos and the traditional videos. Similarly, we develop perception models over the omnidirectional videos that we establish a new video database with some human behaviors like the head movements and the eye movements. And then we propose a reinforcement learning method to model the attention on the omnidirectional videos. And then we developed a subjective and objective video quality assessment methods to the compressed omnidirectional videos. And based on the perception predicted by our model and the predicted quality score of our model, we use them as a guidance to our coding optimization method. And this is the data set we established. The purple regions are the recorded the head movement or the viewports of the videos of the omnidirectional videos, and the red dots inside the purple regions are the collected eye movements inside the viewports. We established the data set like 80 videos from the 58 subjects with 10,000 of frames, and based on the data set, we propose deep reinforcement learning methods for modeling the attention in the omnidirectional videos. We can see that head movement prediction is kind of close. It's very suitable for the reinforcement learning methods because we have in terms of the observation, agent, reward, environment, and the actions. In head movement predictions, the observation is like the viewport, the current viewport the subject can see. And the environment are all of the video frame of the omnidirectional video, including some content we cannot see right now. And the action is exactly the direction and the magnitude of the head, and we need to make some head movement to explore the environment. And the agent is our brains, is our human visual systems, and we can get some reward from the environment to our brains, depending on our actions on this VR videos. So based on this motivation, we developed a reinforcement learning method. Specifically, given a current viewport, take it as the observation of the current steps. We develop a deep thinner network to make some outputs. It includes the direction. It includes the direction of predicted directions of our head movement and the predicted magnitude of our head movement. This is like kind of a policy network in reinforcement learning. And this node is to predict the temporal reward of this step. It's kind of a reward network in reinforcement learning. And depending on this, we can predict the head movement as the action of in this topic and feed it back to the environment. And based on the new actions, we can get another new viewport and put it to our DRL network. And this one is a temporal reward of the each single step. And we also have a long-term reward. That's depending on the when we have a lot of actions and we have a lot of steps, we can obtain a kind of path of our head movement. And this kind of long-term path will be evaluated with depending on the ground truth head movement scan path, and to measure the similarity between them and take it as a long-term reward of the whole method. So this reinforcement learning method has two versions. The one is the online version and the one is the offline motion. The offline motion means we can have the reward of the long-term reward and the current reward because we implement the whole method offline. So we don't need, so we do have the ground truth of the HM scan path. But the online version, we cannot access the ground truth of the kind of overall head movement scan path. So it may be the performance of this is maybe a little bit worse than the offline version, but both offline version and the online version can outperform the shorter methods on head movement prediction. And another work is to conduct video quality assessment on the omnidirectional videos. First, we also collect a lot of videos and let the volunteers to annotate the quality scores of these videos. The collection procedures, including the training session and a test session. In the training session, we will guide the volunteers to how to label the quality score. And the test session, we just put all the videos in a random order and let the volunteers to wrote their quality score. And the whole site, including like 600 omnidirectional videos, and we have the over 200 subjects in total. And here are some analysis on the human behaviors on the omnidirectional videos. We can find that the subject's behaviors behave similar when watching the omnidirectional video, and more than 30% of the image frame of the video frame has even not been watched. So there are a lot of redundancy. And then we use the collected salience map or the human attention to see how the human behavior impacts the video quality assessment. As we can see that this is a PSNR. It is a correlation of the normal PSNR with the quality scores labeled by the subjects. And after we applying the human attention as a weighted map to the PSNR, we can got the weighted PSNR by our salience map. And after that, we can see that the correlations improves a lot when we apply the human attention map. That means the head movement and eye movement maps can be used to improve the effectiveness of the objective VQA on omnidirectional videos. Motivated by the above analysis, we developed a two-stage neural networks for VQA on omnidirectional videos. The first one is we developed a VP9 to make some viewport proposal over the omnidirectional videos. We predict some potential viewports, and then we only predict the visual quality on this is viewports. For the rest of the content, we didn't need to make some precise on it. And the net part is VQNet that's used to predict the visual quality of each viewport, benefiting the silencing map. So the eye movement inside of the viewport. So finally, we can obtain we can predict the quality scores of all the viewports and get the final quality scores over video. That is the evaluation of our method. We can see that our performance can outperform the short-term methods, and even for the accelerate tasks of the viewport proposal and the sensor prediction in our second stage, the accuracy of the viewport proposal and sensor prediction are also comparable to the short-term method. And finally, we just same as the traditional video, so we propose a coding optimization method for the omnidirectional videos by considering the silencing map and also considering the non-uniform sampling of the omnidirectional video. That is in the low latitude regions, the sampling density is significantly higher than the regions at the high latitude. So we consider this in our rate control method. Here are some results. Yeah, here is some published works of this topic. And at last, I want to introduce our new papers of this Cvpr. It will be posted at the Thursday afternoon with a number of 87. We develop a deformable invertible neural network for latitude-aware omnidirectional image scaling. And we developed a inversible framework that make the upscaling process can directly learn from the downscaling process. And we also developed a new deformable-based swing transformer modules to take the place of the coupling layer of the invertible neural network. I'm happy to have you at the post session. Yeah, that's all.
Thank you very much. We are running out of time, so we're going to take just one question. Questions?
So I see that you mentioned there are a lot of kind of human in the loop stuff in your work, like using human as like evaluators or like tracking human behaviors. So do you think like currently with those emerging large models that are kind of mimicking the human behavior or like coding human behavior, they can be used to kind of use as a like somewhere in your pipeline?
So you mean the
like the GPT models?
Yeah, you mean the advanced attention mechanisms for coding the human sense, right? Yeah. It's really interesting. Actually, we made another Cvpr paper last year. So it's about the sensor prediction depending on the transformer-based architectures, and we also use the ground truth silencer to supervise the self-attention generated from the transformer method. And after and when applying the ground truth human silencer to supervise the self-attention inside the transformer, we find that it really makes some improvement on it. So I think the human attention and the machine attention or we see the soft attention or other attention mechanism from the advanced architectures, they can be kind of consistent and they can learn from each other to improve the final results. Thank you.
Thank you very much.
Okay, in the interest of time, while Cvpr is setting up our last slides, I'll start closing the workshop. First of all, let me invite you to give a round of applause to Cvpr for perfect technology setup and everything he did today.
Thank you very much.
It's not an easy task. He's still jet lagged from a long trip and really did a great job there. So in quick summary, I'm really happy, or we are really happy with the workshop. International representation, teams from US, Taiwan, Australia, I mean, really Belgium, really great workshop. We're really happy. At times we had how many Zoom attendees? I remember
20,
seeing
I think so 20 maximum.
20, maybe even more. So that's not bad either. Okay, so moving towards the end here, we will be considering inviting new members for the organizing committee. So don't be surprised if we contact some of you to see if you would like to join us to organize the 20th workshop next year. We will be contacting all of our authors, all of our invited speakers to contribute to a special issue on embedded vision. In previous years, we did have several books published by Springer. We did have several special issues and we plan to do that again. And I think the final thing, did I miss anything? Do I need to say anything? So, yeah, we had, summary. We had 4 papers. We had a number of invited papers. We'll have a special issue. So, yeah, did I miss anything? Probably not. Okay, best paper. Oh, I revealed it. So, the best paper award, it was not an easy decision. So we went, first of all, to the votes by our reviewers and also by the impression we had here. The only presentation among papers that had a demo, we really appreciated that. All of the other presentations were really good and papers were really interesting and really good stuff. But we really wanted to reward the paper that had a demo included. And that's the paper by Yisheng Feng and his colleagues. So if you would step out here, maybe we can take a picture. And I have, I forgot to say, the awards are provided by NVIDIA, really nice development boards, the Orin Jetson developer kit. So that'll be arriving to you in the mail. You will give me the address later. So please come out to get a little token of our appreciation. It's a little NVIDIA pin. I'll just put it on here. Okay. I'll try not to. I lost the other part. It'll probably fall out. Yeah, right here. Hey, don't worry about pictures. Yes. Yeah? On the t-shirt? Yeah. Okay, so let's be careful. Okay. Is your colleague here in the room?
My advisor provides to.
Okay, maybe I can put one on him as well.
Thank you so much. It's my grant.
Okay. And the person who helped you with the demo, I don't see him here, but here is one for him.
Okay, great. Right.
Here's
another.
Okay, very good.
Together, please. Yeah.
Cheese.
Perfect.
Okay.
Thank you. Thank you so much.
Thank you.
for
Really
organizing
great
this.
stuff.
Thank you.
Okay. Finally, the best invited talk. We had a lot of debate. it was impossible to really decide on which one was better or more useful. So we decided to go by a hunch which invited speaker might use that gift from NVIDIA the best, okay? And we decided that it's going to be the speaker who really opened our eyes to enormous challenges that our technology can help with. And I think he will be surprised that he's getting this award, and that's Lars. Please come out. The reason we believe it's going to be useful to Norse Institute is that you guys have research students, that you are not deep into this technology yet, not deep enough, that you have a lot of opportunities. So I'm sure that board will come in handy to your students.
Fantastic. Thank you. Yeah.
Another picture, maybe? All right. So I have a pin for you. Let me just find it. All right. And I'll let you put it on. Thank you. Thank you, Lars. It was great meeting you. With that, I think that's the end, right? Do we have anything else to say? Yeah, we will have another one next year. We are pretty sure. And thank you, everyone, for staying with us to the end. Thank you.
Thank you to Cvpr. He was really the one behind this workshop. Really, without him, it would not happen. So thanks a lot, Cvpr.
Yeah, yeah.
Thank you. Thank you very much.
Once again.
All right. Join Cvpr.
You guys can go now. You don't have to stay for
No, just
all right.
very nice.